Yes, I can just start talking while we're waiting for this. So I'm going to talk about extracting robust information from data, and Rasmus gave me the title, which I like very much. I think it's a very nice title. First, I had no idea what I was going to talk about, so of course I procrastinated on making my presentation. And then in the end, what I ended up doing is I just kind of have a series of comments and thoughts about things I feel like came up in the discussions yesterday. So I'm going to try to sort of talk a little bit about the things that we have already talked about.
Sorry, was something wrong again? Sorry about that.
Well, it's a nice picture you have there.
Yeah, sorry about this.
We are.
No, I think it should be right.
Perfect. There we are.
And 2 seconds and it will be full screen.
Perfect.
Yes.
Excellent. Thank you. Very good. So, just to start, this is Lysefjorden, which is a beautiful fjord on the west coast of Norway. And yeah, so this is a part of our planet, a part of our climate. And we can think about this as maybe the thing we want to learn about. And particularly, we are interested in this little building over here, this little white and red building. And I often feel like when I'm working with climate models and climate data, it is a little bit like my trip out to the West Coast last week. So this is sort of what we have to work with, and we have to try to make the best of what we have. And then my first comment, or first point that I wanted to talk about today, is this thing here. We are interested in how the climate is changing. We want to know for a particular application how our climate is changing right here, because this is the part we care about. And this was a nice little study done by Sebastian Sippel and co-authors, was published a couple of years ago. And this has nothing to do with future climate. This is just looking at historical weather. And what they did is they took a reanalysis product, and then they looked at every single location, so every single grid cell. They calculated the local anomalies at this grid cell, and then they found sort of the distribution of these anomalies across the entire globe. That is what you see here on the left-hand side. And then they compared these two periods, 1951 to 1980, versus 2009 to 2018. And what we can see is that there is not a very big difference between those two distributions. So if we just look at this, it looks like climate hasn't changed very much. But then on the other plot, on the right-hand side, you see what they got when they looked at the global mean temperatures. So they took the global mean temperature anomalies for the same two periods, and here it looks like there is a very big difference between the two distributions. And so we see it looks like actually the global mean climate has substantially changed, and there is not a lot of change on the local scale. Now, if we look at the details a little bit and we look at the axis they have on the x-axis, so what is underneath the plots, you can see that what is here is a factor 10 longer axis than what you have on the right-hand side. So what we have is that the tops between the two distributions are actually equally far apart. It is just that when we are standing in a very specific location, there is such variability in the weather we observe on our body that we don't notice this little shift. Whereas when we look at the entire globe as one unit, then things are much more stable and we see the larger changes. And so this is one of the problems we have, is that people live right here on the left, and they don't notice what is actually happening on the right. And it's sort of hard to envision what's going on. And then the next point I wanted to make, I learned yesterday I should not call this data, I should call this information, because this is really data information here. Now, everyone who works with climate has probably seen this figure very many times. This is from a very well-known paper that came out 10 years ago, where they are talking about sort of the vast differences we can get in climate projections depending on which one particular climate model we're looking at. And so here on the left, we're looking at temperature, and on the right, we're looking at precipitation. And then what we have is we have individual locations, the three top ones here on the left, in North and Central America, and then we have the United States and we have the globe. And what we can see is that for the individual locations, for example, Seattle, the red is the warmest model and the blue is the coldest model. We can see that there's a huge difference in the projection. Whereas if we go to the entire globe, they very much agree. And we can see the same on the right here for precipitation. If we're looking at the wettest and the driest models, which are the red and the blue lines for the future, there can be a vast difference in what these models are projecting if we're looking at individual locations, whereas on the global scale, they very much agree. So it looks like if we need information for a very specific location, that is very hard to get with a single model. And then comes this thing that was mentioned yesterday, which I thought was a very good point, is we need to be very clear about what we need. And this has to be sort of a dialogue between all the different partners in this process, because we don't always know what we need. And we need to have conversations to figure out what we need. For example, here, for, say, precipitation in Seattle, do we really need to know how much it's going to rain in the future? Or do we just need to know, is it likely it's going to rain more or less? Because if that is the information we actually really need, then we can look at the very right column over there, which shows you the results from all of the models. And here you can see that even if there are some models that say it's going to rain more in Seattle in the future, a large majority of the models say it's going to rain less. And maybe that's enough information to answer your specific question. So we always need to have this dialogue of like, what is really the information that is needed? Third point is this thing that decision makers often just need a number, because all they can put into their framework is a number. There isn't space to put a distribution into that framework. And here's an example to demonstrate that even if what you need to get out at the end is just a number, it is important to account for the uncertainties in the system on the way to getting the number. So this example is focused on Bergen. You can't really see what this is supposed to show. So this is a map of Bergen that is very hard to see. And it's in a grayscale that shows elevation. So basically the part here in the middle that you can't see, that is central Bergen, that is very much at sea level. And then it has these mountains on both sides, which you can sort of barely see. And so they are very sensitive to storm surges hitting the center of the city. And then here on the left, what you can see is projections for sea level rise in Bergen towards the end of the century. So that means that they are very likely to see a substantial sea level rise, and that is going to affect damages they get from storm surges. So then we wanted to estimate what is the expected loss for the rest of the century in Bergen due to storm surges. And so for this, we need to know what sort of damages are they seeing now and have seen in the past. So what is distribution of damages? What is the sea level rise that we expect to see? And how is the sea level rise going to affect these damages that they get? And then we put these three things into a model. We made some estimates. And here are two results. So the first black line is the estimate we get when nothing in our model has uncertainty associated with it. We just take median sea level rise, median damage every year, and the effects are always the same. And then we estimate for these 85 years, approximately 50 million kroner of damages. If we then put uncertainties on all these components and combine them, we get a number here that is 9 times larger than the number we had before. So we have numbers in both cases. We just put uncertainties into the way to get the number in one of these. And then I have a question for you. What do you think, which uncertainty component actually has the largest effect on the results? Is it the sea level rise, the damage costs, or the effect of sea level rise on the damage costs? Okay, you can think about that for a second, and then the next slide will show you the answer. I'm not going to ask you to vote, so you can just think about it. And here is the result. So what you see here now is when we just have uncertainties in one of these components. So the green, there is only the uncertainty in the damage distribution. What is supposed to be yellow, uncertainty in how sea level rise affects the damage, and the purple, uncertainty associated with sea level rise. And even if the uncertainty in the climate is very, very important, it is even more important that we have uncertainty in the estimated impacts. Because usually it's the impact distribution that is heavily skewed. It is very random whether the big storm hits Bergen or a different city on the west coast. And then it is also quite random how much damage that storm does. So you can have a very large storm that causes a lot of damage, even if the sea level rise is low in that particular year. And because of the skewness, it is actually the impact part that is the most important one when getting to the final number. So we have to have all of these things together. And then my last component, or last comment I wanted to make, has to do with model evaluation. And the point here is it's complicated. Here is 3 figures from a paper that came out in 2020 by Bach et al., where they were trying to compare these 3 generations of climate models. And so they look at the multi-model mean bias for these 3 models, and then we can look at these maps, and we can see where there are differences and where they're similar. And the issue here is that there is a very large difference in time from when CMIP 3 came out to when CMIP 6 came out. And for that reason, they had to use 3 very different time periods to get these figures. And particularly the time period here for CMIP 6 is almost non-overlapping with the time period for CMIP 3. And so this comparison ignores the sort of inherent predictability of the system at the time for which the comparison was done. So we're really mixing 2 things in here. And so I would argue that this comparison makes no sense whatsoever, even if it's replicated in the IPCC report. And then the other issue we have is with model evaluation. Now, almost all of the colors that are supposed to be in these figures are missing. But you can see the very extremes of the differences. So here we are looking at extremes. So we look at the warmest day of a month and the coldest day of a month for the summer or for the winter. And then we compare the average of these over the period 1979 to 2005 for two different data products. We have the ERA 5, which is a reanalysis product, and we have the Codex 2, which is an observation-based product. And what we get here is, so we have sort of occasional huge differences along the coast because they don't quite have the same land-sea mask. But overall, we see, or don't see, that there is quite a big difference for these two products over this region. And so the question is, what is the truth here? How can we compare our models against the truth if we don't really have a truth? And so my take on that is that we should actually compare them. We should also compare in the same comparison, we should also be comparing the different versions of the truth that we have. And one conclusion is that if a climate model is as similar to some data product as some other data product, then those models are actually doing a pretty good job. And so here are two comparisons where we have the CMIP 5 models in color, the CMIP 6 models in gray, and in black we have reanalysis products. And on the left, we're using Codex, the observation-based product, as the truth, so it has a perfect match with itself. On the right, we're using ERA 5 as the truth, so it has a perfect match with itself. And then we can see the different rankings that we get. For example, we can see that on the right, if we use ERA 5 as our truth, the CMIP 6 models are much better than the CMIP 5 models. And particularly the CMIP 6 models that in sort of foundationally are the same model as the ERA 5 model, those models are doing really well. Which is not the case if we use a totally unrelated data product as the truth. And my point here is that which model lands at the top doesn't matter, because it's not about finding the winner. It really is about seeing what's down here at the bottom to see if there's a model that is maybe constantly showing large divergences from all the versions of truth that we have, and maybe those models should not be used when we're looking at this particular variable for this particular region of the world. So it's really about the bottom and not about the top when we're doing model evaluations. And that was what I had. Thank you very much.
Thank you so much, Tordis. Are there any questions?
Can just say that the covers show up on the Zoom and also on Zoom on the streaming.
Perfect.
I just have to say that we love having Tordis in our projects to help us with the hard statistics. Our next speakers are my colleagues from the... Oh, only Kajsa, okay. The next speaker is my colleague from the Met Office in Norway. She's a senior scientist in the Model and Climate Analysis Group under Rasmus. And she's working on empirical statistical downscaling. I believe she's made this presentation together with Andreas Dobler, who is an expert on dynamical downscaling. So she will show some results in an R-Shiny app, combining the two methods, and the results are used in climate services. So welcome, Kajsa.
Is this the...
Up here.
No, I mean the... Yeah. Okay. Yeah. Yeah, okay. So one of the recurring themes in discussions yesterday was how we as climate scientists can sort of have an impact and reach our intended audiences. And I believe that it's at least a good start to make our results widely and easily accessible. And one way of doing so is to simply put it in an interactive web application. There were some examples of how this could be done presented yesterday or mentioned yesterday. One was the IPCC Interactive Atlas, which is sort of a companion app that came up with the 6th assessment report. In my opinion, a really nice example of how to present data. It has like you can look at a lot of different variables in many different ways, has many different layers of information and types of information. There are also many national climate services that have that present their the regional downscaling in interactive ways, in interactive atlases. This is an example from the Norwegian Climate Service Center. So this app is definitely geared mostly towards, I think, stakeholders like municipalities or people actually needing data for adaptation work. And there were also examples mentioned from Finland and the US yesterday. And here's another example of an interactive app, which is one that Andreas and I and some other colleagues have developed. It's called Gcm Eval. This is an app for Gcm Ensemble Evaluation. It's rather limited in scope. It's meant to sort of support scientists in ensemble selection. So it has like a model skill evaluation, where, as Tordis mentioned, you're not supposed to pick the top 10. It's meant to like get you to deselect like the bottom ones. And then you can also look at the spread of the regional mean climate change. But interactive apps are sort of they're great because you can just start using them right away, but what they have in terms of user friendliness, they lack in flexibility. So there are also many toolboxes available for scientists out there, which connect to big data, to like the climate data store or other sources of GCM data and RCM data and observations and so on. So, and these are just a few. Here are some examples from the Esm Valve Tool. And on the left, a skill evaluation of some models, and on the right, an analysis of the number of consecutive dry days. And so these types of tools typically takes a little bit more time to get into it, but they often have like some recipes and examples to get you started. So when so much is already available, why would anyone want to create another app? Well, for us, it's about comparing information from some empirical statistical downscaling that we've been doing to RCM data, because we want to compare both how using different downscaling method affects the how we view climate change, but also how ensemble selection influences the results. And so we kind of want to provide information for this Climate in Norway report, but the information will, of course, have to be further distilled before it reaches an end user. So the app itself is also more geared towards scientists like ourselves who are working with sort of background information. We're using an ESD method from which was created by Rasmus and colleagues at Met, and there's more information at the end of the presentation if anyone's interested. And we're also using Codex RCM data. So in the many hundreds of petabytes of GCM information or data out there, there is a lot of information, but still in many studies, only one or a few models are considered. So here's an example of how data is used in different building adaptation measure studies. On the y-axis, you can see like the methodological choices, and then you see a progressive loss of information. So, for example, there's only, out of the 132 studies that they looked at here, only 22 considered many scenarios and climate models, and then only 11 actually tried to quantify or describe the uncertainty, whereas as many as 49 studies only used one single scenario, one single model, and omitted to calculate any uncertainty. The problem here is, of course, that running many scenarios and climate models through the modeling chain is too expensive. So we think that combining ESD and RCM can sort of help us with this problem. So we have created an app to test and visualize this idea, where we want to see how much the ESD and RCM results differ and how the ensemble members within the two ensembles differ. So here's just a sneak peek at the app, which is at this point a prototype work in development. So you can look at, you can select either maps or individual stations, and then you see two figures side by side. And then you can select the data source, so then it's ESD or RCM. And then you can select the scenario, and at least for as of now, you can only select the ensemble members for the ESD results. And then on the left-hand side, there's figure settings such as like variable and season. Here's one example from the app. On the left-hand side, you see the ESD results. This is the ensemble mean trend in the winter for the 2-meter temperature in the period 1959 to 2100, assuming the high emission scenario RCP 8.5. And then on the right-hand side, you see the same, but using the Codex ensemble. So now the ESD is based on 81 simulations, but these are 81 different GCM simulations, and the 60 Codex simulations are 60 different RCM, GCM combinations. So it's a smaller subset of GCMs. But all in all, it's pretty similar, and it's kind of difficult to see here, but there are like little black dots here on the right-hand side showing that the results are robust for all, like everywhere in the whole domain, meaning that like a majority, like 90% or so of the ensemble members show the same sign of trend. And here on the left-hand side, the black dots also show robustness. And then for the summer precipitation, the trends look also. Oh, yeah. Okay. Sorry. I see you couldn't see in the last one either. No, that one you could see here. Okay. So this is the ensemble mean trend in summer. On Zoom, you can see the colors. Here live, you cannot see, but I will describe it to you. There's no robust trend anywhere. There's a slight increase in like most of the region, and then like a little bit of a decrease, but not robust, in like Denmark and southern Sweden and Norway. And there are the pattern looks pretty similar for ESD and Codex, but there are like little differences locally. And here's another app. Now you can see the colors. Here, this is from the perspective of a single station. So this is Oslo. On the left-hand side, you see the ESD results. the red envelope shows the ensemble. It's the 5th to 95th percentile, and in the middle you can see like a little weakly red line. That's the ensemble mean, and the black wiggly line shows the observations. And then on the right-hand side, you see the same, but the Codex, and then it's the ensemble mean, but it's the ensemble maximum and minimum. So the ensembles are not showed in exactly the same way. And here, I think compared to if you compare the two, at least the ensemble mean, there's more of a trend in the autumn precipitation in the ESD results than in the Codex ones. And here's another example how you can look at compare different ensembles. So here you see the ensemble trend in winter precipitation in the same period, assuming RCP 8.5 again. And on the left-hand side, on the very left, you see the ESD results using considering all the simulations. And then in the middle, you see just the 10 runs that were included in the Codex ensemble. And then on the right-hand side, you see 5 runs that were used for the Norwegian Climate Service Center calculations. So I think the ensemble mean does not change notably, but there is a reduction in the ensemble, like in the range. So when you reduce the number of models, then you sort of lose some of the information about the range of outcomes. So some conclusions here. Based on our first looks at our app, we can see that the projected climate changes from ESD and RCM show a lot of agreements when the RCM ensemble is sufficiently large. And this would indicate that these changes are robust, at least in the sense that they're not method or dependent. But there are, of course, some local differences. So then this suggests that these local changes are less robust. And what's next for us is to add some features and some variables that we have downscaled, and then to simply clean up the app a little bit and put it online.
Thank you, Kaisa. Are there any questions from the audience? Yes.
Hello? Yeah. Super good work you're doing. I was just wondering, in terms of model evaluation, model selection, you mentioned this Climate in Norway 2100 report. I think you just picked 4 or 5 GCMs there. Do you know why that was done?
There are people here who know more about the ensemble selection process for Klima i Norge. For example, Anita?
Yes, yes. Well, it's a combination of what is available from Codex at the time. So in the last round, Codex did not have a very balanced matrix for the GCM-RCM combination. So it was up to each institution, more or less, which GCM to downscale. Now, in this new round, there's a much more balanced matrix. So there are guidelines on which GCMs to downscale to get a balanced ensemble. But it's also a question of resources nationally. So there's a large modeling job to be done for the bias adjustment and the hydrological modeling of these data. So we need to have a quite limited ensemble. Yes.
Thank you so much.
Thank you. I guess we will proceed with the next task, the discussions on the table. And I think we can probably move around a little bit to get people distributed more evenly. But before we do that, I'd like to say a few words. So today there's a different streaming link that is also provided on the website. So if you press refresh on that, you'll get a new streaming link for today. And also now we have until 11 to discuss around the tables, and that's followed by coffee and tea and some refreshments. I think there's lots of croissants still out there. So we have 1 hour to discuss. I'm going to talk a little bit about the so we're now on T3, that's the task 3. How do we synthesize regional climate information? And so downscaling then involves regional climate models. So we call them RCMs. We tend to say RCMs and ESD. I think it's probably better to spell it out because it's easier for people who are not used to this. And empirical statistical downscaling, ESD, that's ESD, are based on different assumptions, and that's important, and also different independent sets of assumptions. So when they give the same results, then we have more confidence in the results because they are based on different sets of assumptions. And they also have different strengths and weaknesses independent of each other. So that is really valuable to combine these, we think. And I think Barbara will actually say something about that later on today as well. Some experience from Germany. So empirical statistical downscaling may, for instance, be better suited for downscaling large model ensembles because it requires much less computational power, whereas the regional climate models provide a more complete description of regional climate and has other aspects. An important take-home message from DESA, and I really love that you show that, Torres, that the DESA paper is so important. I think also some results are actually generated with the same model, but with different initial conditions. So it's the identical model which gives completely different results on a regional basis. And there's also a DOE number here, because I think it's such an important paper for us when we deal with climate change adaptation. That there are pronounced presence of stochastic variability in local and regional climates, even on local scale. So this is a bit like sort of difficult language for non-scientists, but we're all scientists here. And there's also something I call the law of small number. This is basically when you have a small sample, then you get not very robust estimate of the statistics. So you need sufficiently large sample of independent data to get robust numbers. And this is a challenge. So one proposition is that we get both a clear picture of what a future outlook may look like and get more robust results by combining both regional climate models or dynamical downscaling and empirical statistical downscaling. So this is, of course, up for discussion. So this is something that we want to discuss here now. And we have some questions also that you can read. And I think there will also be some breakout groups on Zoom as well. So you will work with the same questions and same topics. And also you will have some Google Docs that you can write straight into. Please remember to write the names of the people in the group also in the under the heading, so that's it's nice to have some names behind all this work at the end, because we'll synthesize this at the end. So any questions? Good luck.
empirical downscaling results being synthesized into a more robust product. And I guess in that it lies also how can we present it together for stakeholders for climate adaptation? Because what Kaisa showed was two different products. How can we combine them in end product? Empirical statistical downscaling. So that's a method going directly from the GCMs down to local level. So that means that they can, and it's also very
The selection criteria for the articles were mainly twofold. First, they should concern either moisture safety In all, we found 132 studies from the past 8 years, and the research question we posed were designed to Hi, my name is Jørn Emil Gaarder, and I'm a PhD student working in the research center SFI Climate 2050.
we ready? Just before we start, we would like to have a confirmation of who will attend to today's conference dinner. So I sent an email out to those of you who have said you will join for the confirmation, because we are fewer here than we were supposed to be. So if you could just click either I'll join or not join, that's appreciated. And if you haven't get an email and you want to join, just let us know or talk to Christina. And also, And also tomorrow, I'll also find out how many people will join for lunch tomorrow at Øken Portal for the excursion tomorrow. So I will also deal with that tomorrow. So Anita, I'll let you share this. It's actually two talks, and we moved around with the program a little bit. So this will be a very short session, and then we have lunch again soon. Sorry about that.
Yes, I think we have our first digital presentation today. His name is Peter, and I will not try to pronounce your last name, but you could do it yourself. He's the president of European Climate Research Alliance, or maybe known as ECRA, and he'll talk about the use of climate knowledge and information from the ECRA's perspective. Welcome.
Yes, thank you. So I'll try to share my screen now. So let's see if it works.
Yes, it works.
Excellent. So yes, thank you for having me. So my name is Peter Brescow. I'm currently the chair of the European Climate Research Alliance. And I was sort of tasked by Erasmus to sort of give a little perspective on also what we do in terms of our eco development and the white paper. And I think I've sort of been given sort of around 15 minutes. So I've gone down with my sound, so you might basically have to wave or chat to me, because otherwise I get sort of a little echo down here. So I hope everything's fine for you. So the use of climate knowledge and information from ECRA's perspective is sort of the title. I'm basically the elected chair, but also in sort of my professional life, I'm heading an institute at KIT here in Karlsruhe in Germany. So some details regarding ECRA, so just in case you can't, I see. Excellent, thank you, Irene. So some details regarding ECRA. ECRA is structured by collaborative programs, and it is something that's been around for a little bit over a decade. So you can read details in the summary paper by Winfried Hoke that came out sort of a couple of years ago. But it's still sort of structurally sound and correct. So ECRA basically has 4 collaborative programs. One has been Arctic, one is sea level change, one is high impact events, and one is the hydrological cycle. The Arctic is currently reshaped to a polar collaborative program. So that is basically what I'm saying here in terms of transformation of some of the collaborative programs. And I always feel that change is good, it triggers development. And one of the developments is also the development of this white paper, which I come to later. However, some evergreens will stay, and I also will show you something about the biannual journal assembly, which has been incredibly useful in getting sort of buy-in from our stakeholders, the scientists, and the European organizations and frameworks. And that's basically what's in this little sketch here. So basically ECRA is its 4 little CPs that basically reaches into the scientific community and also in the EU with its organizations, but has always sort of an eye on the real world application and societal challenges. So with the structural view, we are basically shaped through our partners and participants and the associates, and currently sort of the thematic highlights are given by the collaborative programs, and we are steered by executive committee. But how does this now relate to sort of the so-called pillars, where we have infrastructure, the global challenges, European industrial competitiveness, and curiosity-driven blue skies research? It's basically that research performing organizations are actually the members of ECRA, But then obviously they're represented by the scientists that are basically driven by curiosity and basically run the infrastructures to actually understand climate change and the global challenges we address by understanding climate change and what can be done in this context. And the European industrial competitiveness is directly addressed by the infrastructures that we modernize, that we keep running, and that we operate. So today I wanted to basically talk to you in this context of consolidating Codex and give you sort of an idea where we are in terms of our process in thinking about addressing the user needs. And one thing that we've done for quite some time now, that we've done also in spring this year, was we run a general assembly where we bring together our stakeholders, our partners, and representatives from the European Union. And this time it was sort of the motto, extreme events under climate change, understanding, communicating, and managing the risks. And I wanted to tell you a little bit more about this meeting. It was actually quite successful and a very nice meeting in the Square Brussels. And you can find the documentation of the meeting here under this link. And we had sort of under this motto, some initial input from John Bell from the European Commission, followed by a panel discussion to do the scene setting. And then we basically went through 3 chapters in terms of the climate processes and research needs, basically addressing what do we know, and basically where do we basically have to focus our research. Then we basically talked about the risk management aspect, or what do we need. And then there was one thing where we basically wanted to address the limitations and uncertainties. So how can we put things together? And all this discussion was then actually the trigger for sort of a white paper that's still in progress, and that's kindly edited by Rasmus. And I also hope with these nice presentations I've seen here so far, we can take some input and go back to this white paper and advance it. One thing I wanted to note was that the explaining limitations session was actually quite interesting as well, because there for the first time we also tried a direct link to sort of climate psychology. So how is climate change perceived, and what do we do with those informations? And sometimes I don't think when we break down climate information to very small scales and make it very personal, then obviously also we have to accept that people get worried about the information and really ask themselves, what can I do? So I found this quite interesting to actually get a better feeling for basically how information that we produce from our data is perceived and what people then do with this perception. And so we had a nice question and answer session with the attendees following those 2 presentations we had by Per and Judith. And afterwards we had quite good discussion in the breakout groups. So I found this very, very interesting for me to really better understand what people expect and make out of information that they maybe have never even asked for. However, basically the white paper we sort of then started is basically really on this broad subject on regional climate information for society. That's basically how the current working version is coined. And obviously what we do recognize is that we have a diversity of communities and that we need to provide bridges from science to society, but also in between the communities. Basically, we should ask certain questions, and obviously there's the obvious ones, but sometimes I always find it also important to spell the obvious things out. So one would be sort of what knowledge and information should be used and how, and can we provide some guidance on how to use the right climate information and how it can be used in the best way. And that then actually goes all the way down to perception. So if the information is there, basically, what is the end user actually making out of this information? Given our structure in this respect, we consider the different collaborative programs individually. And as I've already told you, sort of the one that basically is changing currently is the Arctic Climate Stability and Change, where we basically see a refocusing of research needs, and thus basically also the name of the collaborative program has been adapted to really highlight those changes in the research needs. Sea level change and coastal impacts are presumably very obvious for many who also live in coastal areas. It's always a worry, what will happen next when I have the next storm surge, and what will happen generally under climate change when sea levels are really rising, and what do we have to do? Changes in the hydrological cycle, I think, are also of interest to many of us, and we've seen this in certain flood events and with strong precipitation. And the more generalistic part is sort of the high impact events and climate change, where really the questions are asked, what are the high impact events in a now actually faster than ever changing climate? One obvious link that we build also over the last couple of years in a quite regular way is that the latter two CPs, changes in the hydrological cycle and high impact events and climate change, are usually collaborating very closely. And also this year, they participated, or we participated, in the Climate Change and Water Extreme Events conference in Tours in France. And so we had there a little ECRA session where we also basically looked really at sort of examples of vulnerability, and had also a practical example from the agricultural sector, basically what kind of informations are urgently needed to, for example, make wine production more drought-proof. It's always quite interesting, and then obviously provides feedback to us in terms of science requirements, things that we need to address to be better. So also we've heard a lot already about sort of different strategies of using climate information, and it obviously starts with things like the downscaling itself. It has been addressed here extensively, because obviously the coarse resolution of a global model isn't good enough. So we do sort of downscaling for regions and very local venues. However, what I find sort of very important with a slightly different hat on is sort of that we have a traceable methodology. And also there, I think we can help on an institutional level by basically making everything we do in terms of the downscaling very transparent, that we provide open software, that obviously, regardless of what kind the method in detail is, statistical, partial differential equations, what have not, there always is a chance to basically redo it with either new driving data from the global models, or basically just repeating it for the sake of being sure everything went right, and then improving what has been done. So open software seems to be very important. And also touches on fair data. And for those of you who might not have heard about this acronym, I was wondering if I should have spelled it out on the slide. It's basically findable, accessible, interoperable, and reusable data. Because really what we need to generate the information is that our data is findable, needs to be accessible, and obviously very importantly, if I really go towards the product, the data needs to be interoperable to make new avenues of research possible, or also new products possible. There may be slightly unusual things come together. So I think the I in terms of interoperability is quite sort of an important thing that we need to address in more detail. And what's incredibly important, and it has been mentioned already also, is sort of the dialogue with stakeholders and the society. And we do have different stakeholders and societies on different levels within our organization. And so we need to understand what information and knowledge have decisions been based off in the past, and what is always sufficient? Are there gaps that we need to address? We also need to understand how changing weather and climate affects the decision making, and how different should the information be to basically allow you to actually come to a new conclusion and to sway a decision that you've taken earlier. So that's basically sort of more of an update cycle in terms of when new information becomes available, how do we deal with it? So what is if the information was actually wrong? And how do we deal sort of with this uncertainty that there is obviously a margin for error? And does it always matter? Or is it more sort of the direction is important and not always the quantity? And that's something we have to explore. And also in terms of how we communicate uncertainty we have to progress still. I know many of us work in this area of communicating the uncertainty, but I think there's certainly more we can do to make it even clearer. Before I really close, I wanted to give you one personal idea of what I'm doing, even though it's not particularly ECRA. But remember, I also told you in the beginning that in ECRA, the foundation science does play a role, and it's the infrastructure, the blue sky research that comes together and creates data and information. And so I wanted to give you one example of downscaling, which basically is an example I quite like in terms of a lee wave in the lee of the Antarctic Peninsula, where we basically modeled the ice clouds. And that's basically sort of the downscaling example, where we go from a global model, which you can see here, to a regional nest. And you see the global, Antarctica, and then the region of the Antarctic Peninsula shown here. And not surprisingly, if you have a lee wave, this ice cloud in the lee of the Antarctic Peninsula gets more pronounced when the resolution is lowered. And that's compared to a just global one, where nothing happens. And here we do have two-way nesting. And that's why I show it to you here, because what you see by what happens with the two-way nesting is that actually the small-scale ice cloud becomes visible in the global model as well. And that structure here is informed by the smaller scale, and that's not the case here, where we just run the global model and we have no refinement and there's no two-way interaction. And so the point I wanted to make is about this two-way interaction. It's important for the physics that we base our understanding of and generate the data, but it's also very important for basically exchanging information. The person that provides the information needs the feedback from the person that uses the information. So two-way interaction is always important. And with this, I would like to close. We thought I'd say 15 minutes, but I'm not over too much. More information. So our webpage is up. Please feel free to contact collaborative programs directly if you're interested in their content. The white paper continues thanks to Rasmus on regional climate information for society, and we are progressing there well. And basically, the outlook is that we run hopefully in 2024, if COVID allows, our biannual event again, and the preparation will start with the next XCOM meeting in early December. And with this, thank you for your attention, and I'm obviously open for questions and happy if you have any questions, please feel free to contact me. You find me easily. And by the way, we are still looking for a new secretary for the European Climate Research Alliance. So if you would be interested in this position, do contact me as well. Thank you.
Thank you so much, Peter. Are there any questions here or in the chat? No? Then I thank you for being with us. Yep. And our next speaker is here, I think, Barbara? Yes, Barbara Fru.
Thank you for having me. Cheers. I go to the other stream now.
Thank you. Barbara is a senior scientist at Deutsche Wetterdienst, and she works on downscaling, and she'll also show some experiences from DWD on joining statistical downscaling and RCMs. So your presentation is ready here.
Ready here, but not there. Do I have to do something?
Maybe the technicians will help us. There.
Ah, yeah. Okay. Thank you very much. I'm very pleased that I. You need okay, Mike.
Mike, or maybe a headset.
You can have mine.
Oops. Like this? No, like that.
Yeah.
Okay. Yes, here. Yeah, I hope you can hear me. Thank you very much for the invitation, also to present our view from Germany on this issue. It's only a part of my presentation on the combination of empirical statistical projections and dynamical projections, since, well, we do it just. Yeah, and but I want to share with you our experience from more the application rather the research. And yes, okay. Then let's start. Yeah, so very important as a national Met service is, of course, the interaction with the users. And so climate change is so to adapt to climate change is prescribed in many regulations in EU, in Germany. And so there's a lot of interest in getting good information on climate change. And therefore, in Germany, a group with a representative from federal states and the federal government was set up already 20 years ago to exchange the views on the use of climate projections and also requirements for climate adaptation. And this group is rather active. They meet twice a year. Also during the pandemic, they met virtually, but now again, they meet in person. And they already defined some guidelines for the use of climate projections. So it exists in German, but also a peer-reviewed publication with a link here. So it might also be interesting for you. In addition, we conduct annually a user workshop to discuss the needs from different sectors. And there, every year, some new users come, and so the first discussions start with to make them aware that some of their decisions really depend on the climate. So they are used to a stationary climate, but this is not the reality currently. So we have to discuss in detail the impact of the changing climate. And of course, there's an intensive dialogue with the users to gain an understanding of their needs and to also discuss limitations of the climate information available. This is very important that we understand what the needs are. So, and this extensive exchange I described the slide before is well, the basis for all the activities I'll describe below. So I'll start first with the contributions to Codex we have at DWD. So we are currently developing ICON as a limited area model, but also ICON seamless. So we bridge the gap from the one society to another, or we try to by combining the regional and the global scale. And this model will be applied. We will have one model for data assimilation, for weather prediction, for climate projections, for climate predictions, and also for air quality simulations. And we want to have a consistent model for all these time scales, spatial scales. And of course, we need different configurations depending on what we ask for. But the idea is that we have a model as similar as possible and also to minimize, of course, the effort of maintaining this model, but also that the answers are more or less similar for each question we pose. We do not do that alone, of course. For the ICON CLM, the limited area mode of ICON, we're working closely together with the CLM community, and also with for the global mode, we also work together with the Max Planck Institute and also with KIT, where Peter is situated, and also with the German Climate Computing Center, ICARA-SET. So what we want to contribute, or what we contribute to EuroCodex, is on the one hand side the simulations, the climate projections at 12 kilometer resolution, and we will contribute with ICON CLM and with a coupled model, ICON CLM, coupled with the ocean model NEMO. And we also contribute to the flagship pilot study on convection permitting climate projections. And yes, this is rather a research activity currently, I'd say. But it is very important that we have this activity in mind for future also climate services, because our users ask for even higher resolved climate information. And therefore, we need this kind of experiments. But as you see here is the domain of what we use for this flagship pilot study currently. And you see that well, all countries are somehow cut, so it's not if you go for these kind of simulations for a single country, then you will hardly have any exchange with other countries, because the focus will be on the nation, to be on focus, and this might be a problem for the future. In addition, we have the empirical statistical downscaling method. We call it episodes. Maybe you heard of that. The idea is that we will build up, or will support a resilient ensemble for regional impact modelers and decision makers. And we want to increase the available ensemble by adding these statistical method climate projections. The requirements we have for episodes, for the generated data, for example, from the hydrological models, is that we have transient data at least at a daily basis in high spatial resolution. And what we also have is, especially for hydrological models, they need consistent sets of data. So for all the data used as input for the hydrological model, we need physical consistency between them. Otherwise, will not result in a good data. And this multivariate consistency of the data should be at least for regions as big as the large hydrological models, for large river catchments. And of course, with the statistical models, we can say that they are more or less free of any systematic bias, which is a big advantage of them. And well, we think with these requirements to the empirical statistical method, we are allowed to combine these climate projections together with the climate projections from RCMs. Okay, we talked about the speed of the statistical models, and is very high. So in fact, we already downscaled all the available global climate projections from CMIP 5 and CMIP 6 with episodes. So it's a, well, rather quick activity. So the most effort is on getting the input data ready for processing. This climate projection we want to add to the Codex ensemble. Currently, we have for the CMIP 5 ensemble, we had about 11 GCMs and 12 RCMs. I'm not sure I computed it right. And in Germany, we have 2 statistical methods available for CMIP 5 and several scenarios. But as you know, these climate projections do all have issues. Some global climate projections show poor performance for Europe, and some regional climate projections show poor performance for Germany. So as a consequence, we noted also in the Codex community that we have to have more careful selection of the global projections from the CMIP 6 for downscaling. And I think for CMIP 6, this was well done in the past. So I think this is very good step forward for all the activities we have behind that. In addition, we are making we have to make a quality assessment of the regional climate projections for Germany. What do we understand with that? We want to have plausible climate projections for robust information on the climate change. Of course, all these assessments should be transparent and publicly available, as documented, where all the deficiencies of the climate projections are listed and why they are withdrawn, for example. But all the climate projections passing this quality assessment build what we call reference ensemble. So the method is we have two-step quality assessment. The first step is more technical quality assessment. So are all variables available? Is the coordinate system correct? And all these things. And this referred to a general usability of the climate projections. Is a minimum requirement. It's not really a quality, but it's just are the requirements fulfilled? So are all these the protocol of the simulations fulfilled? In addition, we have a more physical or process-oriented quality assessment, and there we want to withdraw all the unplausible climate projections. For example, a wrong annual cycle, or all these things which lead to very bad information. Then, but of course, everything is focused on Germany. We do not make any statement about the quality of the climate projections outside. So it's really with a focus on that. And with that methodology, we, out of the 29 historical runs we investigated that time, so it's a couple of years ago, 19 were identified as problematic for Germany. And this is a rather high number. So it's more than half of the climate projections which we defined as not to use for climate impact studies in Germany. Okay. In addition, so we have this 19-member ensemble, but our users say, well, that is much too much data. We cannot handle that. And so they request for a small ensemble, and we thought about that. And then we developed a method, or we developed a core ensemble. And for that, we developed a method where this ensemble is reduced by withdrawing all the redundant climate projections, but keeping the essential information preserved. So what we did is for a couple of variables, we computed the distance between two climate projections, and if the distance is low between them, we define them as very similar and skip one of them. So because this is, of course, we were talking about the difference between data and information. There's a lot of data, but the information we gain by additional climate projections is poor, and therefore we skip it. And with that, we reduced this 19-member ensemble to, depending on the question we were asked, to 5 or 6 climate projections, representing about 90% of the spread of the reference ensemble. And here's listed what we checked with that. But in Germany, we also discussed that with the climate projection, there's no probability of occurrence with each of them, but we only can get the information of the spread of the ensemble if you go that further. So that also means that all these mean values and all these things doesn't make sense, but you only have to be aware of the minimum and the maximum of the spread. But of course, this could differ for different variables, regions, seasons, whatsoever. So it is not like you have the one climate projection giving the maximum and another one the minimum, but it is really, depending on what you are interested in, it differs, and you have to keep it in mind. So it is not the message that all these information are, the climate projections in between are not needed anymore, but except the ones with a very small distance to others. But we need this core ensemble in total. That's the message from that. Okay, we just checked it for the additional principles, and unfortunately, there was not much information, more information coming through the principles climate projections than was already available there. For Germany, of course. This is also only for Germany. We didn't check it for other regions. It's only for Germany. And might look different for other regions, other similar simulations, and so on. What we did with the RCM climate projections is a multivariate bias adjustment. So with this bias adjustment, we can also easily combine them also with the empirical statistical climate projections, and that's what we did. Unfortunately, with this, as I explained, with this reference ensemble, we have currently 4 different reference ensembles in Germany. This was not by intention, but this was just maybe because of the parallel developments at different places, parallel development for similar things, for similar issues. And for the CMIP5 ensemble, we now have these 4 different reference ensembles, and because of the very specific user requirements. So you know that the quality assessment is very different for different regions. So if you're in the mountains or on the seaside, it looks different. And of course, users also have different priorities for that, if they are responsible for the coastal area or the Montanas. And some of them, they also need, for certain reasons, certain periods, like the 1961 to 1990, and this is only for not many RCM climate projections deliver that. And some say that they need a very large ensemble, and therefore the empirical statistical methods are added, and so on. For CMIP6, of course, we aim for one uniform reference ensemble, which makes life much easier in Germany, hopefully. And so this is very important to have, because the impact of climate change is very much depending on the ensemble I choose. So we saw it. If you analyze different ensembles, you get completely different information, and this is very hard to communicate. And therefore, we aim for one uniform ensemble that we can speak with one voice. And so a coordinated effort is ongoing, and I hope we will succeed by that. And I think, I come to my summary of experiences. So at first, users have very specific requirements, and sometimes they formulate them very clearly. An intensive user dialogue is crucial, because we need to learn what they need. Also, quality assessment is key to provide resilient climate information. Like Kaiser also showed that with the least GCMs, which shouldn't be considered, but this is going to the same direction. We use both RCMs and ESD climate projections, as it is a basic requirement for many users to have a large ensemble. We aim for nationwide uniform reference ensemble for uniform climate information. Ideally, this also applies to the neighboring countries, because if we at Austria and Switzerland, they are speaking the same language, at least partly. And so it's difficult if they have completely different recommendations than we do. And therefore, it's also an agreement with the neighboring countries, especially when they speak the same language. An international cooperation for a balanced and resilient ensemble is crucial, since currently we do not have the perfect model, which would be necessary for having a single model ensemble. And we need to find a path for the convection permitting simulations, also in an international collaboration, from my point of view. Uniform and coordinated information from climate research is also very important to reduce the communication difficulties. So if from all communities the same message is transported, then people are not, weird by that. And also simple communication helps. So it's not necessary that we explain the complexity of the climate system, but only how climate services can be used for climate adaptation. And that's what I wanted to say, and I thank you very much for your attention.
so much, Barbara. Any questions? Yes.
Actually, two questions. One is on the seasonal and cadal predictions, which is, as far as I know, rather challenging. So what's your thoughts on that? Because there's a lot of demand for it, but a lot of people that don't want to get into it because it's very challenging. So that's one question. The other is, maybe you said it and I missed it, but what do you mean with a resilient ensemble?
Okay. First question, so some people dare to get involved into seasonals and decadals, but we are. So we are providing seasonal and decadal forecast on operational, rhythm. Of course, it is difficult to communicate because very, very similar to climate projections, you cannot refer to a single date and say, it will be raining between 12 and 1 o'clock on, in May. But if you analyze the information seriously, then you can get a lot of information from that. So I think it is still a little bit on a research mode because the predictions, the skills, the forecast skills are rather low compared to weather forecasting. But if you go back to the 60s of last century, then you find very similar skill scores as well for the weather prediction. Of course, we will never get this sharpness of a forecast as we did with a weather forecast, but I think we have a lot of potential for deducing information which is really, really important. And so this winter in Europe, I think it's everywhere, we have a lot of pressure for forecasting the winter. Will it be warmer than usual, colder than usual, and so on? And I think there's a lot of research needed also for finding ways of improving the information which we can deduce from the data we have. So this is not easy, since at the moment we forecast for the seasonal forecast, for example, 3 months mean. But I think that the energy demand will be decided by the cold air outbreaks. If we have 10 days of a very, very cold period, then this might be decisive for the energy consumption. And all these things need to be developed and need to be checked and all these things. And, I'm optimistic, otherwise we wouldn't do that. But there's a lot of work to do. And the good thing by that is that we can enhance the forecast skill very easily because we are so low. So we have a lot of potential. So.
But it's meaningful, at least already now.
So yeah, we are very hesitant with publications on that. But our summer prediction was very good. So we had a very hot and very dry, so dry that we didn't dare to say it loudly, but in the end we were right. Maybe for the wrong reason, but it was a quite good forecast. So and we are quite confident that we improve it even more, going to extremes like cold air outbreaks and all these things. But this is research to be done. And with resilient ensemble, I mean that currently we rely on the ensemble we have, and we deduce the uncertainty from the spread of this ensemble. But we have always to be aware that it is only the knowledge we have. And with a resilient ensemble, I mean an ensemble which is not changed dramatically by putting more data in. So like this principle runs, so they are, from the one-hand side, of course, a little bit disappointing because they do not add, so for Germany, always for Germany, yeah. They do not add information for Germany, but on the other side, this makes a bit more confident that the existing ensemble is really resilient. So like we can deduce the information we need from that. So it's yeah. But it would be a bad sign if you would add one or two projections and then everything would be the other way around. And this is what I mean with that, yes. Thank you. Okay.
Okay, any more questions?
Yes, I actually had a question about the core ensemble.
Yeah.
I was just wondering, do you do that selection or reduction from 19 to 5-6 simulations before you do the whole bias adjustment, hydrological modeling part?
Yes. Yeah. So we do it before the bias correction, but after the quality assessment.
Yes.
So we withdraw the unplausible simulations for Germany, and then we make this core ensemble investigation.
Thank you.
Welcome.
Yes.
Thank you, Anita, for chairing this session, and also thank you, Barbara. So we on purpose did plan a lot of breaks for this workshop so that you have the time to talk together and discuss things. And we already have lunch. We just had refreshments, and I think we sort of missed a little bit on a number of people who come physically. But so there's plenty of food here, and now we have an hour to mingle and have some more food, hopefully. So yes, but it's actually very good food. It's a yeah. And then afterwards, do you want to say something, Irene? Yeah, so it's three quarters of an hour. So that's good. And also, I would like to remind you to send, respond to the form about the conference dinner. So then Christina gets a total overview of the number, because we are about 1/3 of what we thought, or half of what we thought we would be here. So some people didn't show up. So, okay, enjoy.
Da ist Bill schon mal. Okay.
Skal vi se for når straks den er klar her, nå får legen inn i den.
Ja.
Så nu skal jeg...
Får ikke det fungere nå. Andre veien.
Det er liksom fel håll. presentasjonen.
Jeg venter på. Jeg står og venter her. Rasmus, si for meg klart det. Men du får jo, hvis vi skal si det, så får du ikke vist både dem og prestasjon samtidig. Vi får ikke sett både de og prestasjonen samtidig.
Nej, det kanske... Men vi kanske kan... Jag bara presenterar några bilder och sen kan vi komma in.
Jeg skal bare laste den her.
Okay, so let's start. This next session begins with a panel discussion, and now the panel is online. And I will introduce those people after a while. I thought I'd show a few slides first, and then I will introduce our panel. But meanwhile, I will tell them welcome to our panel, and let's see if we are missing someone or if everyone is here. Okay. Okay, so I wanted to start with reminding you about this image that I showed yesterday. The chain of from global to local. And where there's global models, regional models, very high resolution dynamical models, the empirical statistical downscaling models, and also we are moving into Earth system modeling. So there are lots of challenges to face. And this is an overview of coming Codex simulations, downscaling of CMIP6. So here we have listed people who have committed to do downscaling for certain areas. And should say that there are still some areas missing. Here there's no one who committed to doing downscaling for Africa, for instance, so far. And it seems like most people will do for their own region, at least to start with, and then perhaps they will go on to do for other regions as well. But this is actually a problem now, that no one committed to do for Africa so far. These are a list of some emerging issues in downscaling. And there are white papers, Codex white papers, and the Codex science plan that list these issues or how to try to deal with these issues, which is of course also then part of how we plan the downscaling of CMIP6 and what to do with that afterwards. So it's smaller regions, higher resolution, and how to weigh between this and focusing on physical processes, etc., so that everything can't fit in because we don't have resources for everything, for instance. And the added value of downscaling, what we have been talking about now, the distillation of various methods and various information and data, for instance, and the scientific challenges and societal needs, how to bridge the gap, for instance. And there are also then this about observations and how we use Earth observations in Codex. And how, with Earth observation here, I mean space-based Earth observations. We had a small survey, and these were some of the challenges that emerged: accessibility, resolution, reliability, missing variables, and inconsistent and limited time series cropping options, for instance. Those are some issues that people said were challenges for the regional downscaling community, at least with using space-based Earth observations. Now, something also that we've discussed partly here is what do we know what climate we should adapt to. So this is also an issue to take into account, that it's really important to know what we should adapt to. And here's an image to show what it can look like with and without knowledge, how we can plan our cities, for instance, if we have knowledge or if we don't have knowledge, the difference between those. Now, this is the panel. Marcus Thatcher, Chris Leonard, Maria Laura Bertolli, Daniela Jacob, Bill Gutowsky, Koji Dairako, and Dalian Sheng. And I think I didn't see Koji, but maybe he's joined us now. I can't see Koji, but maybe he'll come in later. Okay, and then I just wanted also to show the one more slide, just listing, reminding you about the panel 2 discussion, what it's about. So could you show just the last slide also, and then go back to, these are the issues to discuss in this panel. So what's the status on downscaling and climate services in various regions of the world? And how do we combine and use data or information from various sources? And how can we improve availability, adequacy, etc.? And how we integrate multiple data, and how we look at compound events, both physical or natural compound events, and if we combine these with socioeconomic events as well. So these are some of the issues to discuss in this panel. And now please go back to showing the people in the panel. And now I will start with asking all of you to say a few words about what you do and how you look at these issues in general, and then we will move into more detailed discussion. So I will start with Daniela Jacob, who is one of our Codex co-chairs. Please go ahead, Daniela.
Yeah, thank you very much, Irene, and hello to everyone. Thank you for inviting me. I'm a meteorologist, expert in regional downscaling, dynamical downscaling, and I work now very closely for the climate services and sustainability and transformation. So very closely connected to adaptation activities and the need for delivery of data. A statement which I would like to make here and trigger a little bit of the discussion is that I would never use GCM data directly for adaptation option development. I think this is very clear, and the local and regional setting and the local microclimate is so important for the questions to be asked and the adaptation options to be decided, that it is important to involve local knowledge, local stakeholders, and the best information you can ever have. So regional downscaling, local downscaling is important, ideally connected with some statistical information. And I think that is what we need to do, and to inform society, I would say, transparently about what we know. We know much more than what Irene just mentioned. And I think we achieved a lot in the last years, and we can deliver information in a trustful way. Thank you very much.
Thank you, Daniela. And then I would like to move on to Bill Gutowsky, who's a former co-chair of Codex.
Yes, thank you, Irene. I'm Bill Gutowsky. I've worked for a long time in regional climate modeling, and in more recent years, my work is focused on extreme events, diagnosing events, storylines that emerge from that, and then even beyond that, working on co-production with partners out in the broader community who would want to work with our data. And I really want to emphasize the importance of co-production, which is not simply providing data or even developing a linear supply chain, but actually co-developing the knowledge, the data, the understanding with our partners, taking advantage of the wisdom that they bring into this whole process. And I'll leave it there for now.
Thank you, Bill. Then we'll move on to Maria Laura Bertolli, who is one of our points of contacts for South America.
Okay, well, hello, everyone. Thank you for the invitation. Well, my name is Maria Laura Bertolli. I'm from Argentina, from the University of Buenos Aires. as Irene said, I'm a point of contact of Codex in South America domain. I work with statistical downscaling specifically, and my interest is in climate variability and change and extreme events. But that's it. Thank you.
Thank you, Maria Laura. And then we could move on to Deliang Chen, who is a leader, one of the principal investigators of the Codex flagship pilot study, and have also been involved in a lot of other things. So please go ahead, Deliang.
Thank you. And I just follow on a little bit what Daniela said about the GCM, usefulness of GCM. And I think we, even with the normal or conventional regional time model, is not good enough. So I would go one step further. And because as the Codex, for example, the standard one maybe is like 25 kilometers or 10 kilometers. But when we're dealing with, for example, mountain regions, very complex terrain, etc., you have processes. You also have the need for applications that needs much more localized scenarios, and a lot of needs for the extreme events. Even in Europe, when you're talking about the extreme events, that we know that you will not catch the really heavy precipitation if you don't go to the convection scale, permitting scale. So at the same time, we also know that all the models are wrong. And so the observations should play a bigger role. That part, I think the statistical downscaling or analysis can really add value if used properly. And my final point is that what we did in Sweden over the last 10 years or so is that we use both regional climate models and statistical downscaling. And we use statistical downscaling sometimes to actually pack everything together. And because we have too many scenarios, many roundings, but users that are very difficult. So, but we could use the statistical method to package them into something as a function of global temperature, for example, which is much easier because there are so many scenarios that for many users, they are not very keen. They just know, okay, if we have 1.5 degree global warming, what we should expect. So I think that part is the statistical analysis can be really useful. So I'll stop here. Thanks for more questions.
And next speaker, I would call on Marcus Thatcher, who is a point of contact from Australia.
Yeah, so I'm Marcus from CSIRO in Australia, having mainly a background in dynamical downscaling methods with regional climate models. We've been involved in, well, there's a number of regional climate modeling groups in Australia, and we try to form a partnership to make sure that we're coordinating those experiments and getting the most value out. So there's a tendency to use multi-model approaches, particularly for national challenges like federal government, state government initiatives, or electricity sector type projects and those sort of things. So there's a lot of good coordination and trying to take advantage of the different modeling capabilities that we have.
Yes, and then lastly, we have Chris Leonard, who is a former Science Advisory Team member and now a point of contact for Africa.
Thanks, Adrian. Yeah, I'm Chris Leonard. I work at the University of Cape Town in South Africa. Daniela, I did have a chuckle at your comment because then don't read Working Group 2 at all. Yeah. What do? On paper, I'm a downscaler, I suppose, but we also are in that co-production space that Bill was talking about, where we don't believe a website portal is going to give the user what they need. We have to first together understand what folk need in terms of climate information, and then see if we can actually produce that. But understand at the same time that in their context, perhaps climate information is not important for them at the moment. Yeah, but I'll stop there just so I can give the discussion an opportunity to flow. Thanks, Ian.
I don't know, can you still hear me? For me, it sounds a bit strange now. Okay, great. Now, actually, the discussion is free, but I would like to hear what the rest of you think about what Daniela said about that the global models can't really be used for adaptation. I would guess that most of you agree, but please go ahead. Someone wants to start?
Yeah, sure. Can you hear me? What I would say is I largely agree with Daniela. I think we have to think about what processes we're talking about. If you're talking about teleconnections, things like that, well, you need to have the global models there as part of the backdrop to that at least. But ultimately, yes, the information that you need to be developing with your partners has to be obviously pretty regional. And global models just don't have the resolution to capture usually all the relevant processes that affect a region's climate, especially if you want to start talking about highly impactful events.
And then I will let someone else in, but I would also add, so how would you say that you would combine GCMs, RCMs, and statistical methods in the best way? Because we heard Barbara Frew earlier, for instance, talk about how they combine it, but I forgot actually to ask her, what did she mean with combining? What does that actually mean in practice? So I would add that question to the thought about using global climate models for adaptation.
Let me just come in here for a second. I, of course, make this provocative statement here in order to get the community being pushed. And Chris, I'm glad you mentioned Working Group 2. I fully agree and I'm fully aware of this. So, and Irene saying now combining dynamical and statistical downscaling and Bill having the global models in the back is all correct. And it's all needed. What I do want to point out here is that there's a difference between scientific analysis and scientific development and development of information on which decisions are based. And in order to overcome these difficulties, I think it's important that we push more strongly towards the local information and the co-production, as you said, Bill, and of course, from the connection from global to local and local to regional and regional to local. So all is important, but I think if we could cross a bit more through the disciplines, get in closer contact with hydrologists, with ecologists, with infrastructure people, and have them be part of the discussion, and we are part of the development of the adaptation options, we can make a big difference. And at the moment, we are too focused to, which is good from a science point of view, but we are focused on how do we connect statistically and dynamical downscaling and to make the best out of it. But I think the next 5 years need another gear here with different communities, and that's what I wanted to push for. Thanks.
Then I will ask the rest of you, Maria Laura, Deliang, Chris, and Marcus, to comment on this as well.
Yes, well, I agree with Daniela, and I think it is important also the coordination, the collaboration, especially in regions like South America. Creating and networking with the co-production is essential to get that objective from the very beginning, right? Because the statistical downscaling community in South America is very small. So we are trying to push that community to grow up, and I think it is essential to do that from the very beginning with the co-production. I want to say also that I'm the principal investigator of the flagship pilot study in South America, the Codex flagship pilot study in South America, where we are doing that. We are working with two impact modelers that use the simulations we are performing. And we design all the experiment with a co-production from the very beginning, including and discussing the modelers that we are using our data. So the coordination is very important. The collaboration and the discussion and the networking is also very important in our regions. I think in all regions, but in this region where there are many gaps in this knowledge and these communities, this is a very foundation. So, they are the funds for this road.
Yes, thank you, Maria Laura. And before moving on to the rest of you, we should welcome Koji Dairako also, who now joined us. Seems you had some problems, Koji. So would you please say a few words about who you are?
Okay. Hi, thank you for your kind invitation to this panel. I log in and log URL. Sorry for delay to log in. I'm Koji Dairako, Associate Professor teaching University of Tsukuba, Japan. So my research background is regional hydroclimate science, in particular dynamical statistical downscaling and hazard and risk assessment. And one of the contacts work on Codex in Asia. Also, we are working on capacity building through PBL project-based learning, Japanese government scholarship program, and we hope continuous efforts of capacity building to foster collaborator in the world and to continue networking. Okay, thank you very much.
Thank you, Koji. I think the sound was a little bit bad, so I didn't hear everything you said, but I think I caught the essence at least, and I hope the rest of you did as well. We were just discussing things like can you use GCMs for adaptation or not, and how do you combine information from statistical downscaling, RCMs and GCMs, and also how to work, cooperate with users, etc. So this was the discussion, just to get you into to the mood here. And so I will ask the rest. It was Chris and Marcus. Do you have any comments on what Daniela and Bill and Maria Laura said?
I guess I'd just comment that we find all the information sources very useful. As I say, it depends on the scale and the process, but definitely there's value in that. And we tend to use GCMs to get the large ensemble, and then the downscaling to kind of get the information, local information, and the impact kind of scale work. We also tend to work with knowledge brokers a lot to try and get a very good engagement with the stakeholders early on. And there are natural tensions in that process between how much the information is, say, simplified and how much the integrity of the information. But I think we get the balance right, but it is a process, and some energy and time and resources need to be put into that.
So before we move on to the rest, with regards to that, could you also say something about, do you find it difficult to get the stakeholders to come to meetings, to engage in this?
Often they're funding a lot of these projects, so they're very engaged because it's often their funds, and so it's just getting the breadth of stakeholders. But often there's a bit of a, almost knowledge exchange where we have to try and explain the limits of the climate science, but we also need to understand their domain expertise and what the actual vulnerabilities that they have, so that we're identifying the right climate variables and we're targeting the right information in a way that's coherent for their application. And I tend to find that can change significantly from project to project. So sometimes people want to boil it down to a single number, and we've been involved in projects where they didn't want us to calculate, return periods. They just wanted the raw petabyte of data, thanks, and they'll take it from there. So it's quite a mixture, and this is where I found knowledge brokers really invaluable because they've been helping us navigate that complex landscape.
So we could say that value for money is a big part of this also.
Yeah, well, I think to make a measurable impact, so it either affects policy or an adaptation strategy or something like that, like there's a measurable impact, and often linking into different levels of government is important so that it actually has impact at the scale where people that are actually making decisions will use the information.
Thank you, Marcus. And I will ask Deliang and Chris if you could also give your take on this.
Maybe I can start say a few words. I'm sorry, I see now I am doubled actually in the system. I don't know what happened. Hope you don't hear a lot of echoes, which I hear here.
No, I don't hear an echo.
Okay, good. Yes, it's very complicated, I would say, and the influence policy we talked about. I think it's maybe in terms of downscaling, maybe in my experience at least, it's not so relevant. But these are mainly determined by the larger scale modeling and the studies. But to influence the stakeholders and also to be influenced by the stakeholders, I do feel is very important. That's our experience, that we have to engage them from the beginning before we do the downscaling, because that will influence a lot of choices, because in the work we have to make a lot of choices in terms of how many GCMs, how many samples, and what is kind of information for uncertainty that are relevant to the stakeholders, and what are the information they really need, because sometimes we do produce a lot of information that they are not using. So it's challenging. I hear the word tension, but for us it's not tension, but it's mainly the different interest and the different language and the different experience, and then also different expectations. To align all this, I think the only way is to have the interactions with them from the beginning to the end. So the co-production is also very important. I think that has been mentioned by some other panelists, that we need to think about all this. But otherwise, I think I share many points that has been said by my colleagues here. So thanks.
Thank you, Deliang. Chris, do you have anything to add to this?
Maybe just that the ability to get information and data/information varies across where you are. So for us, it's very difficult to get climate data and store it locally, or run climate models, or even get a hold of usable climate information or develop it in a co-production. I mean, we do champion the co-production narrative, but it's hard when you go to start from the beginning every time. So it's challenging. It is the correct way, I think, but still it comes with its challenges. Yeah.
When you say start from the beginning every time, what do you really mean with that?
Oh, just that I think Marcus mentioned it, you've got to, as a climate scientist, try and convey the understanding that climate models and climate information can only take you so far. And then we as the climate scientists have to understand the context that we're working in. So we've got to learn something too. And and then you build forward from there. But it takes time and effort, and we find quite frequently actually that we're expected to do this without getting paid. So government agencies or donors, or I won't mention any Met offices, expect us to do this without any remuneration. And it's really hard. I mean, we want to do it because we know that there's a community that would benefit from it. But at the same time, we do want to get paid for it.
Of course. Yeah, and I'm sorry to say, but we ran out of time for this panel discussion now. So I'll just ask if there's one final comment for someone, and then we need to move on to the next item on the agenda. So any final comment? If not,
I could jump in. Yeah, I think we're talking about hearing what our partners are doing. I think we also need to think about how our partners inform our model development and the design of our simulation programs. That it's really a not even just a two-way interaction, but multiple pathways of interaction that are involved.
Thank you, Bill. And with that, then, I thank you, all the panelists, for being part of this. Thanks for your views on this. And we will probably come back to you. You will all be part of, or your input will be part of a report after the workshop. So thanks a lot, and let's give a round of applause for our panelists.
Thank you very much. Bye-bye.
Thank you very much. And then the next item on the agenda is a breakout session, and I think Christine will inform a little bit more about that.
Okay, thank you. Is this on now? Yeah. I'm not sure if you want. Will you put up the table discussion on? Well, I can just talk it through. So we'll start now with the table discussions, table 4 discussion, on how should different sectors make use of the information if you were the decision maker. So to say, so based on your own experience as a climate scientist and or decision makers, what information would you need for the following cases? And exactly what would you do with it? What do you see as challenges now and in the future concerning climate and weather? So, what the plan here is that you can either choose one of the points below. You pick one case each, or if you decide for one country at the table, you can try to address all of the cases. We added also one extra case, number F, or not a number, but the letter F. If you were the university professor responsible for developing or building a master program in climate and health, what competence education would be needed? But the other ones are then also A, responsible for public health in your country. If you were CEO of an energy company in your country, or if you're head of the city water management in your country, bureaucrat for the building sector regulation in your country, and nature conservation in your country. So pick and choose, or address all of them if you have the time. So yes, please. I guess you will have all the breakout rooms at Zoom, but otherwise we have the tables. And you can swap around if you like. So, yeah. So let's go ahead. Thank you.
Rasmus kommer sen. Rasmus, skal bare begynne. Okay, people, I hate to break up these good discussions, but we have a time and an agenda to go on with. So if the technical could please show my screen. So, welcome to the next session here, where we are going to have some early career scientists presenting. First one will be a video presentation that I got on this computer from Jørn Emil Gaarder. Then Emir Ahmed will be the next one on Zoom. After a coffee break, we will have 2 presentations in the room from Vincent and Sophie. And in the end, I'm not sure if Shilpa will agree with me calling her early career scientist, but she couldn't make it yesterday. So we took the liberty to adding her to the program today at the end. So the first one is Jørn Emil Gaarder, use of emission scenarios in the climate models in building adaptation research. And if I can get this running now, and the technicians can get the sound on, I hope things run smoothly.
My name is Jørn Emil Gaarder, and I'm a PhD student working in the research center SFI Climate 2050. The focus of my PhD is climate adaptation of buildings, both to local climate and to future climate changes. Together with Hans Olav Hygen in the Norwegian Meteorological Institute, among others, I have reviewed the published literature on the subject of climate adaptation of buildings. The selection criteria for the articles were mainly twofold. First, they should concern either moisture safety of buildings or energy and ventilation calculations. And second, they should use future climate models as part of the methodology. In all, we found 132 studies from the past 8 years, and the research question we posed were designed to first map what methods were commonly used in order to analyze how uncertainties from future climate modeling were treated and communicated. Because, as most of you probably know better than me, introducing future projections will introduce a host of uncertainties in the results. This graph is made by Meskani in the Norwegian Meteorological Institute and shows the variability of different types of downscaled climate models for Norway concerning temperature development. This graph is produced under scenario RCD 4.5 by empirical statistical downscaling. Blue represents 9 projections for Norway that have been dynamically downscaled and bias corrected. Red is the same model statistically downscaled, and orange presents the full range of GCMs statistically downscaled for Norway. And this is only the variability within one climate scenario. Before getting to the climate model, you will first have to decide which climate scenario to use, which of course is based on complex socio-economical developments for the next 100 years or so. Adding to that, in the other end, is the need to produce a weather file. Because when considering the moisture safety of a building part, it's not enough to know what climate it will be exposed to. You will need to produce some sort of explicit combination of temperature, wind, and rain that varies over time. So to sum up, when using future climate estimations for building adaptation research, you will need to consider the uncertainty level of your results to know how strong your conclusions are. And 2/3 of the review selection are studies concerning energy calculations and heating and cooling loads in buildings, and the remaining third are studies concerning moisture safety and other deteriorating effects on buildings. This ratio is partially an artifact of the search method, but also an expression of the relative sizes of the research areas. The studies looking at energy demands are mainly concerned with future projections of temperature. There is a need to know other factors as well, such as wind and relative humidity, but these have very limited effects on the results. The studies looking at moisture performance, on the other hand, are dependent on reliable projections of rain patterns especially, which have larger uncertainty levels connected to them compared to temperature estimations. Approximately half of all the scenario calculations used are based on RCP 8.5, or the earlier equivalent scenario. This is the worst-case scenario presented in the IPC 5th assessment report. For studies looking at a single scenario, over half of the studies used RCP 8.5, while the studies using multiple scenarios usually calculated RCP 8.5 and compared this to one or more other scenarios. Typically, RCP 8.5 and RCP 4.5 were compared. Worst-case scenario calculations can, of course, be useful as a conservative design choice, but it can also lead to development of solutions that are too extensive. In such cases, climate adaptation measures may be at odds with climate mitigation measures, since more comprehensive solutions often results in higher emissions. But more troubling is that 9 of the studies in the selection did not even specify which future emission scenario they used as a basis for climate estimations. When the basis for the future climate scenario is unknown, it is impossible to say if the conclusions of the study is overestimating or underestimating the effect of climate change, and any treatment of uncertainties becomes impossible. In the next couple of slides, I have sorted the different studies into subcategories. These categories are not mutually exclusive. Some express the type of study and some express different methodological choices concerning climate modeling. And the purpose was to see if any of these subcategories correlated with different uncertainty treatments. The categories are mainly based on scenario choice, downscaling methods, and type of study. And you can see here how many studies fitted into each category. For instance, many studies used a single scenario, they used statistical downscaling methods, and they predominantly used a single GCM with a single initial condition to produce future climates. This diagram shows the different methods for downscaling in detail and the ratio for each of the subcategories. The green part of the columns are dynamic downscaling, which is the most comprehensible method. The only category that used predominantly dynamical downscaling from multiple GCMs were studies concerning future climate loads for buildings. Typically, studies calculating future driving rain loads or snow loads and such studies. The light gray part of the columns are studies that did not describe their method for producing future climate models at all. In total, 15% of the studies did not do this, and mostly they were studies of future energy calculations, which only needed a future temperature estimate to apply to their models. The diagram on the left describes how uncertainties connected to the future emission scenario choice was handled, and likewise to the right the climate model. And the gray part is no mention of uncertainties and variation. Blue is description of the variation with no further handling, and green is studies calculating uncertainties in some way, usually by calculating variations from different alternatives. What is interesting here is the progression, which becomes even more apparent on the next slide, which describes the uncertainty treatment of the results. There is a 3-step accumulation of uncertainties, in a way, involved. First, you will need to choose a future emission scenario. Then you will need to choose a method for expressing future climate based on that scenario. And finally, you will need to calculate how this climate affects your results. The progression through these 3 steps are easily seen by the growing of the gray parts of the columns. The column on the right expresses, the column on the left expresses all studies in the selection. About 70% of the studies had an explicit view of uncertainties for emission scenarios, but only 50% showed the same tendency when it came to the climate model. Evaluation of uncertainties in the results, either through qualitative analysis or calculations, were performed by 35% of the studies in the selection. Another 20% mentioned that climate model uncertainties were an unknown factor and a limitation to their particular study, while 45% of the studies did not mention future climate uncertainties at all in the results and conclusions. This can create a false impression of certainty in the results. And through this study, it is my belief that there is a need for method development to express uncertainties better in such studies. There has been a lot of work on mitigating this when it comes to climate modeling, but unfortunately the availability of climate models and weather files that handle uncertainties properly and explicitly is low. The studies that presented a comprehensive uncertainty analysis also usually concluded that this had a large impact on the conclusions and should not be omitted. Building adaptation researchers are, of course, not meteorologists, and making comprehensive climate models for each study may prove difficult or impossible. But one way of expressing some of the uncertainties involved are to use multiple scenarios and multiple climate models where this is available. Then variability between different alternatives can be calculated and presented in the results. As this graph shows, 11 out of the 132 studies went this path, while the vast majority of studies went the path of single scenario and single climate model. Of course, all good research involves methodological simplifications of reality in order to produce results. And in complex matters such as this is even more important to even get a result. But the more simplifications are made on the way, the more information is lost in the results. And when making such simplifications then, it is even more important to be aware of what is known and what is not. In that way, at least uncertainty analysis of what you don't know becomes possible. That was all I had. And I'm very sorry I couldn't be there in person to answer your questions, but I have allied myself with Hans Olav Hygen for this purpose, so I hope he can answer anything you're wondering about. So, thank you for your attention.
Yes, and I hope nobody has any difficult questions since I'm Hans Olav. But I find it quite fascinating from us working on giving out more and more information, wider and wider spread, a huge amount. And then it comes down to the impact researchers. We take one single. I think we have a challenge there. The next speech is Emir Ahmed August, the use of climate data for projecting Earth-slide risk. He is on Zoom, so please, or at least should be on Zoom.
Yeah.
Yes.
Hello. Can you hear my voice?
Yes, we can hear you, nice and clear.
Perfect. So do you also see my presentation?
Yes, everything is fine. So the floor is yours.
Perfect. And it's on the presenter view, I guess. Yeah. Hi, everyone. I'm Emir Ahmed Oğuz, currently working as technical engineer at NGI. Today, I would like to make a presentation on the use of climate data for projection of landslide susceptibility. This study was from my PhD at NTNU in Klima Digital project. This is the content of today's presentation. I will first go through background and the motivation of this research. Then I'll go through the use of climate data in landslide susceptibility analysis, and then I will conclude my presentation with some remarks. Landslides are worldwide problems causing fatal events This is worldwide distribution of the events in between 2010 and 2014. Almost 9,000 people died every year between 1995 to 2014. And majority of these events are associated in time and place with extreme rainfall events. These are two examples from Norway, which occurred recently due to extreme rainfall events. IPCC report shows that there will be more intense and more frequent rainfall events in the coming years, excluding some parts of the world, of course. But for Norway, this more intense and frequent rainfall events will increase the risk associated with rainfall-induced landslides. So this requires better understanding of climate change on landslides and explicit quantification of climate change impact on landslide susceptibility. We should do this to mitigate the upcoming risk of rainfall-induced landslides due to climate change. In this study, we investigated a study area which is prone to landslides in Trøndelag region, 45 kilometers east of Trondheim. There are 3 weather stations that we found to be proper for this study. And in this figure, you see some dots, which are the grid points of EuroCordex dataset. In this study, we used modeling framework, which includes both climate modeling chain and landslide modeling chain. I will first go through the climate modeling chain in more detail. We can start with the climate modeling. Yes, emission scenarios are used to represent how different technological and social developments can lead different greenhouse gas emission scenarios. And in this study, RCP 8.5 was utilized. This assumes no climate policy, high population growth, and slow technological development. Global circulation models are used to evaluate or provide future projections at coarse resolution by using key global physical and chemical processes. Then the regional climate models are used to provide finer resolution projections based on the boundary conditions from the global circulation models. For Europe, there exists an ensemble of projections called EuroCordex, which includes 56 projections, including 22 regional climate models applied to 8 global circulation models. In this study, we have utilized this EuroCordex ensemble of projections. The effect of climate change are integrated in landslide modeling by using intensity duration frequency curves. These curves relate rainfall amounts with its duration and frequency of occurrence. These curves were constructed by using a quite straightforward, nice formulation proposed by the researchers from Meteorological Institute, Rasmus, Kajsa, and others. This formulation provides the rainfall amount for a given duration and return interval. It also includes 2 correction factors, which are obtained by the data fitting. And mu and FW are the main parameters in this equation. Mu is the wet day mean precipitation, and FW is wet day frequency. These are the parameters which change within Norway, and these correction factors are pretty much the same. So when we obtain mu and FW for present and future time, we can obtain climate-dependent IDF curves. An example is illustrated here. Blue dashed line is for present, and red continuous line is for future IDF curves. Then we can integrate these IDF curves in landslide modeling chain to provide landslide susceptibility maps at a future time. By using this equation, we investigated 3 time periods: present, near future, and far future at 3 weather station points. First, we investigated the change in two parameters, what they mean frequency and what they mean precipitation for 3 weather stations at near future and far future. And now using the pairs of these two parameters, we can obtain the IDF curves. And these IDF curves are obtained by using the ensemble mean of these 56 data. Later on, these IDF curves will be used in landslide modeling. Very briefly, I can mention about the study area from landslide, from geotechnical engineering perspective. Here you see the slope map over the study area, and the dark red parts are steep slopes along the river. It's quite a landslide prone area. There are different soil types, which were simplified into 4 for this study. This figure shows the landslide events occurred in this study area from National Landslide Database of Norway. And they were used to calibrate the landslide model in this study. So when it comes to integrating climate modeling data and landslide modeling data, this study proposed a probabilistic framework which integrates the uncertainty in both climate model and landslide model. This example IDF curve is 2D graph, but actually it has a 3rd dimension, which is the probability density function of the rainfall events at present and future time periods. When we see it on 2D, we see that there is a shift in PDF curve towards right, which means that high rainfall amounts become more probable due to climate change. And we can obtain these IDF curves by using pairs of what they mean frequency and what they mean precipitation. And we can obtain different pairs of mu and FW by assuming a Gaussian distribution using 56 projections. And this is the formulation that we proposed to integrate the models by accounting the uncertainty in them. So briefly, this is the probability of failure maps from the landslide modeling chain. And this part comes from climate modeling. This probability of density of a certain intensity rainfall comes from the PDF. And this is the probability density function of mu and FW pairs, which comes from this Gaussian distribution. When we integrate it, we obtained overall probability of landslide initiation at a given rainfall duration. Briefly, I will show some results for 12-hour duration rainfall events. In this case, we investigated the intensity range over this line. And just to show for the illustration purpose, I just selected very small representative zone over in this area, which includes both soil types and very steep slopes. This is the probability of failure map for this representative zone at present, near future, and far future time periods. The red zones in these maps are getting darker, and the extent of red zones increase. But it may not be that clear, so we can see the statistics over the whole study area. This table shows the mean value of probability of failure at 3 time periods for different slope range. For example, from present to future, there's a probability of failure, which is the average over the entire study area, goes from 20.6 to 23.6, which means 3% increase in average over the whole study area, which is quite high. When we see we can also observe that the maximum increase in probability of failure might be up to 10%, which is quite high. In addition to that, we can also see the landslide susceptible extent over the study area, which is the extent with a probability of failure greater than a certain limit. There is no common understanding of this limit, so we can employ different probability of failure limits. For example, if we say 30% is the probability of failure limit, so that we can decide the susceptible extent. So we see these results. They represent that at present time, the extent having a probability of failure greater than 30% is almost zero. But until by the end of this century, it will be around 10, which is 100,000 square meter. We can also employ different probability of failure limits. The susceptible extent level change, but we observe the same with time. There is an increasing landslide susceptible extent due to climate change. And such explicit quantification of climate change shows us the critical zones in a study area so that we can make some mitigation studies to prevent or mitigate the risk to society. Two major conclusions. This study was the first study which attempts to integrate climate modeling into landslide susceptibility assessment by considering the rainfall events with their corresponding likelihood of occurrence. And this proposed integration framework shall lead to more accurate detection of critical zones, and therefore a better strategy to tackle the upcoming risk can be developed. Thank you for listening. And if you have any questions, feel free to ask, please.
Yes. Yes, thank you, Amir. And we have some time for some questions. I think there was one in the chat, but I haven't got it yet. So is this on? How do I turn it on? Yeah.
This is a curious question. If you have talked to users or decision makers about these results, I'm just wondering if they would think that 3% sounds, how do you say, not enough to make a change in decisions, so to say. I mean, I could imagine that that would seem little, even if it's not.
Thank you for your question. That 3% was the average over the study area. So the maximum increase might go up to 10%, which is, in my opinion, quite high. So I wouldn't live under a slope which has 10% probability of failure. And the decision makers should also consider this. So definitely there will be high risk, but of course the increase in the probability of failure also depends on the methods that we use in the model. So in this study it is 10%. And for example, if we have a design, a construction work, which is specifically designed for certain return interval rainfall event, in that case, for example, 50-year return interval intensity rainfall events, the increase goes up to 20-25%, which is quite high and should be considered in decision making.
Yes. Thank you. There were also a question in the chat from Amelia Remedio from Codex. Thank you, Amir, from detailed presentation. Did you get hourly precipitation data from the Euro Codex simulations? And did you do any bias adjustment?
Thank you for the question. So it's a nice question. Yes, we used EuroCortex data for the future projections. And it includes 56 projections in total, which were not bias corrected. We could also use bias corrected data, but the number of projections will decrease. So we selected the higher number of projections instead of limited number of bias-corrected data. But in order to address bias correction, we used delta change approach in the study.
Okay, thank you. Rasmus has a last comment here.
Yeah, she also asked the question whether we used hourly data for Eurocodex, and we didn't, because if you look at these IDF curves, you see that they have a very simple form, and we downscale the shape of the curves rather than hourly data. So if you look at, with this formula that we have, that's all we need is actually daily data to in a way extrapolate to sub-daily, because we see that these IDF curves have a simple form, and we used IDF curves that Julia, who's here, has generated from Norway, and we use them to calibrate to actually, so this is like a semi-empirical theoretical result, this curve. So then that means that we can downscale the shape of these curves, and then we only need daily data to make some inference on sub-daily. It's not perfect, but if we have nothing else, this is maybe the best we can do. And it gives fairly useful results when we tested it.
Okay, then I think we break for coffee, half an hour, and then we have 3 more interesting lectures afterwards. Hello. Yeah. Then Rasmus is back, and we can start up again. Okay, welcome back to the last part here. I promised you 3 lectures. Unfortunately, the one that was delayed from yesterday has to be cancelled. She is not feeling well. But the first one today is Vincent Pons, using climate information for assessing green roofs. And yeah, please come forward, and we have to give you a microphone, and I shall find your presentation. Yeah, that one. Okay. Yeah, you have to control it here.
Oh? Ah, yeah, okay, sorry. Okay, can you hear me? Yeah. So today I'm going to talk about green roofs and about how which study we did to try to predict the future performance of green roofs, but more generally it could be extended to green infrastructures because the difference between green roof and green infrastructure is sometimes just a few other hydrological processes. But before going into detail, I just want to introduce you a bit to the way stormwater is managed those last years in a lot of European cities and European countries. And I think it's in general in the world the way we are going towards in terms of stormwater management. So basically we have different type of rainfall events, and we use different solutions to handle them. So first we have like the day-to-day rain, and those rains we just try to store the water permanently or to remove it permanently from our sewer system by using evapotranspiration or infiltration. And then we have major rains. So major rains, there is always a discussion of which probability of occurrence we should consider. But so it depends a bit on decision maker at that point. But the goal there is just to attenuate them as much as possible to lower the stress in the sewer systems. And then finally, we have these extreme events where the traditional approaches like sewer systems cannot handle them. So we know that there will be flooding, and we just have to accept that our infrastructure will fail. So then at that point, the goal is to ensure safe floodways, so to accept that some street will be flooded, so that we have to look at it. So what I'm going to talk about is mainly green infrastructures that are mainly used for this first step. The interesting thing is that often they are designed for the second step, even though by concept they are useful for the first step. But that's, I think, some stuff we have to change in the guidelines in the future. So green infrastructure, basically, the idea is you have precipitation inflow, and you will try to use evapotranspiration and infiltration to remove as much water as you can from the sewer system. And then, by the water flowing in the medium, you will have some runoff out of it that will go to the sewer system, but that will be attenuated from the precipitation. And the thing is, for this process, we need some different resolution. So, for instance, for evapotranspiration, I would say that daily resolution is enough, let's say, because the thing that we have to consider is green roofs are quite small, like, for instance, 100 square meter. So they need very high resolution data in terms of temporal resolution. So the point is, for runoff and infiltration, what we need as input is minute resolution data. So we've been working on that question and trying to develop a framework to go from the green infrastructure design and try to see how we can address all of those different steps with different methods. So some are based for the step 1 and step 2 mainly on continuous simulation with a long-term time series. And then when we want to look at more extreme rain, we have to look more at extreme events. So we developed some methods to sample some extreme events. So When we look at observed time series, the thing that we don't have yet, I would say, in the guidelines is all the information about this kind of stochastic uncertainty, this climate variability, and it's something that needs to be represented in the green infrastructure performance. So that's what we have been working on. And then when it comes to go to projection, then of course there are other sources of uncertainty, like linked to the scenario, linked to the process we used when it's about statistical downscaling. And those also needs to be accounted for in the green infrastructure performance. So I'm going to talk a bit now about the time series use, and later on I will talk about the extreme events. So basically, when you want to know how a green infrastructure is performing, you just can use like various metrics, but one easy way to do it is just to measure the total amount that goes in your infrastructure and the total amount of water that goes out of your infrastructure. But often, when people try to assess the performance, they will just take all the data they have and get one number out of it. But the issue is that then it doesn't represent all this climate variability. So what we suggested here was to use cumulative distribution, basically. So it's just like having, let's say, 20 years of data using a moving window to have like for different years, for different period of time, a different annual retention. And when we do that, so here it's in the case, I think it's in the city of Trondheim. So that's why the retention fraction is not that high, because in Norway, due to the climate, like the proportion of evapotranspiration is not that high if I compare to more thousand countries. But what you see is that the range of retention is mostly between, let's say, 20 and 35% of retention. So when you look only at the mean, at the single number that you take from this time series, you only get to, okay, let's say 25%. But this doesn't represent, like again, like this climate variability. So we try to convince a bit more decision maker to look at the full range and to then create a threshold that is based on the range of performance that a green infrastructure can have. So that again, this case is for like for evapotranspiration. So it's not that much linked at that point to downscaling, but it's something that we have to take into account. But when we then go more to, we don't see very well on that on the slide, but I will explain. So when we go on to more the discharge that the runoff that goes out of the green roof, often the practice will be to look at only, let's say, so survival distribution or flow duration curve, depending on how they call it. But if you look only at that number, so let's say the probability to, like the amount of time per year above 0.1 millimeter per minute, if you look only at one number, you could get here in this case 21 minutes. But then if you take into account the climate variability, you will obtain a range between 5 and 100 minutes, let's say. So that's that type of information is more valuable for the decision maker, even though they don't like it when you tell them that it's uncertainty and so on. But we have to try to make them understand that they have to base their decision on not more complex data, but more reliable data, I would say. And then when we move from that to downscaling, we have like on top of that climate variability, we have all the variability that will be linked to the ensemble and to the downscaling process. So it gives us a bigger range, but those range can be linked to a kind of magnitude, let's say, of occurrence that we want to represent. So the point is, depending on the type of event, you're not looking for, you don't need to be at minute accuracy for something that is around 1 hour. Like when it's around hour resolution, you want to quantify in terms of how many hours per year you will have this, you will exceed that threshold. So the accuracy we need depends on the end use of the infrastructure, And so it means that mainly for extreme events, we will need probably a higher resolution and higher quality data to do that. So yeah, and yeah, the take-home message on that is like basically with if we only consider limited data and if we ignore this variability, the end user, like the decision maker, will just base decision on wrong kind of performance evaluation because they don't represent the full picture, the full behavior of the infrastructure. And another thing, so I don't want to go in detail of the downscaling that we did, but basically an interesting thing is that among the different time series we used from Norway, for instance, most of the range, the uncertainty, was linked to the ensemble of model and not the downscaling we did from daily resolution to minute resolution. So I thought that was interesting. And then also this ensemble uncertainty was a bit bigger than the let's say the observed stochastic uncertainty we had on the observed time series. So we have those different, let's say, source of uncertainty at different stage of the process, and we have to chain all of that to try to quantify estimates and to have like order of magnitudes that decision maker can base their decision on. So now quickly we'll talk a bit about extreme events. So basically, when you want to deal with extreme events in stormwater management, you use IDF curves, such as the one that have been presented before, I think. So what we did in our case is we couple IDF curves with the use of statistical downscaling model. And this statistical downscaling model allows us to sample for, let's say, a day of precipitation, let's say 70 millimeter, for instance, in one day. We can sample a lot of probable heterographs. So, of course, the downscaling model can be always improved and will be for sure improved in the future. But the interesting information there is the fact that since it's a stochastic, it's a weather generator basically. So since it's stochastic, you can sample a lot of heterographs, which allow you to evaluate your infrastructure in a lot of different ways for a large range of possible extreme events. So basically, that's what we did. And here I just show like a cumulative distribution. So we sample basically 1 million, for instance, of extreme events with the same total depth, and we look at the peak runoff for all of those events. And then that gives us, for instance, a probability to be below the threshold that a municipality would formulate. That also allows us to study how the infrastructure behave in this functioning domain. So functioning domain is here when we are below this probability threshold. And then the last thing that is quite important and that needs to be accounted for a bit more in the future is this failure domain. So how the infrastructure is behaving when we are above the peak runoff. Because often the infrastructure are designed sometimes to resist, which means that once you exceed that threshold, you will have a way higher peak runoff. So the shape of the cumulative distribution will have a break in terms of slope when you reach the failure domain. So that's also something that we need to account for because we want to know how much infrastructure can contribute even for extreme events. And then, so a few words to back up a bit all of that. So basically, we need like different data for stormwater management, different information. And those are like basically time series that we need to address day-to-day events, and we need them on minute resolution. But we are also interested a lot in extreme events to study probability of failure of different infrastructure. And the main challenge for us now is to put that a bit more into guidelines, to have like the natural viability like more represented. And I think that this kind of stochastic generator are very valuable for us. I mean, even though we could have like in the future a better, higher quality projection at very high resolution, we can still see a value in using stochastic generator. It's very useful for them. And the last thing is that I think that instead of just trying to have climate scientists bringing their results just to the door of, for instance, stormwater management. We should maybe rethink together, because sometimes the practice in stormwater management were based on the data available in the past, and now if we have better data and more methods available, we can just rethink all of that together. Yeah, and then it's 2 studies that we did link to that. So yeah. So if you have any questions.
Yes, thank you, Vincent. It was very interesting. And if there's a very quick comment, we have the time. If not, we are, yes. Microphone.
Maybe I missed it, but which models did you use?
For downscaling, you mean, or?
Yeah.
So basically, first we used the data that were available in Norway at the grid data from a Codex, but at 1 kilometer regular resolution. And so you had 10 models available, so we took all the time series that we could. And then after that, we used multiplicative random cascades to downscale to minute resolution. Yeah.
Yes, thank you. Then we prepare for Sophie, that's going to tell us more about pesticides and climate. I'm just going to change the presentation here.
Do I need to hold it, or
Okay.
I'll leave it here?
You can leave it there if you stand still.
Yeah.
You have to use the computer anyway. So, well, the floor is yours, Sophie.
Hi, thank you very much. Sorry.
Was it a mic? It was a microphone. Yeah.
Yes.
Okay.
My research usually focuses on risk assessment of pesticides, and I'm trying to use a probabilistic approach and with a Bayesian network. So probabilistic risk, pesticide risk assessment has 2 parts, exposure assessment and effect assessment. So this presentation will be focusing on the exposure part of that assessment. And for pesticide transport in the environment, usually there are a lot of processes involved. So you have like spraying of the pesticide on the field, and then they leach to the groundwater, or they are exposed to the surface water by surface runoff or by drainage, or they are they drift away with the wind. And then there are other processes involved, like degradation or absorption. So there are some ways to predict the exposure of pesticides in the ecosystem. And these are some commonly used models. The focus one is mentioned in some of the pesticide regulation frameworks. But then there's also the rice water quality model, the river water quality model, and for Norway there's a WISP model. And these models try to integrate these different processes that you have seen before on that really small figure. Like they also take into account the soil properties at the sites, and they're very temporal and spatial dependent. So the different models have different focus on time and spatial area they take into account. So I will explain what I did in one of my studies. I used the WISP model, and we tried to predict the exposure to the surface water near Syverud, which is a field near us. And we developed scenarios dependent on the soil in that area, the pesticide application, the crop type that was used, and then also the chemical properties for the pesticides. And we had also some climate conditions that we used to run that WISP model with. And this is an example of the input that we had from the climate models, which was just pesticide, the precipitation, the evapotranspiration, the temperature, the wind, and the radiation. And for 26 years at a time, the model was run. And we looked at the time frame from 2000 to 2100. The input is quite simple. We only had 2 climate models available at the time, and it was enough to develop our overall concept. So that's why we didn't look into more climate models or an ensemble. But this is the output for the WISP model example, which is the predicted exposure in the stream. And then you have the exposure for several days at a time. Like this is the peak concentration, so that's like the day of application, and then it looks at it over 90 days. And then for the RISE-Q, which is something we used in a different model, we have the predicted output for also a couple of days after application. We further looked into some of the relations between how the application or the amount applied interacts with the climate at the time, so the precipitation or the temperature. We still need to further explore that relationship, but that's a work in progress. And this is the example output for the study we did. So we have the Bayesian network that I used. We have the exposure distribution for the day at a time, and we can derive a risk quotient, which is usually used to estimate if there's a risk to the aquatic ecosystem. So if there's a risk, if the risk quotient is above 1, there is assumed to be an effect or risk to the aquatic ecosystem. So as you can see for these 2 scenarios, so this is the current situation compared to the future situation with a higher application, the risk increases a little bit for the aquatic ecosystem. I tried to gather together what the limitations or possible future improvements are for what we have done. And one of the limiting factors about this model we used is that it is quite manual, and that the format it requires as input is very specific. So you cannot just go ahead and just grab whatever new climate model you have to really tailor it to that model, and that's one of the limitations. And for the climate models we used, we also didn't manage to bias correct them. So that would be a next step to use bias-corrected projections instead. And then we also need to further explore the relationship between the climate conditions and the pesticide emission. Oops. So then I have another example for the RISE-Q, which is a model that predicts the concentration in a rice field. And this is a study done together with MDA Aqua, and it's a lake near Valencia. It's called Albufera. And there are a lot of rice fields around this lake. It's a wetland area. And they use this tool, AutoRISE-Q, which they developed with CodeLine and Python. And they predicted the exposure for 550 different fields in this area, and the exposure of the pesticides. And they also developed scenarios. For this also, we only had 1 climate model available. So again, it's a bit limited in how much climate variables we can take into account at the time. But it's more about the concept in general. So once more data is available, especially with Bayesian networks, you can easily update the networks. So what we then looked further in is how these different differences in exposure for the different times we predicted the pesticide exposure for affect the different biological endpoints. That model also has some future improvements. As it works with CodeLine, we can apply more or various different climate models in future, so it's more automated, it's more easily run, and the format of the input is much more adjustable to what is available. So it's a bit more promising. And then, yes, I have overall general data needs that I try to describe for what we do, and also discussed it with some of my colleagues. And in general, what we currently encounter a lot is that there is no one archive that we can look up climate data that is easily accessible and understandable for us to use. It's a very specific terms that are used, and for me personally, that's my limit. I cannot understand those terms. And then there was also like a need for more accessible, like if there is a archive that we could access, how do we compare the different models? Is there an easier way? So a colleague suggested that maybe there is a need for like a R Python package that is making it more accessible and easier for us to understand how to visualize the data and how to compare the data from those databases. And then there's also a need for like a more time-specific downscale climate data for, like a weather generator in general, Thank you for your attention.
Yes, thank you, Sophie, for a very interesting talk to see more on the application side of the system.
Yeah.
It was very good. Thank you. Any questions, comments, anything, Sophie? Yes. See if I can get this on and not destroy it.
I'm sorry.
Yeah, I was just thinking that maybe that's what you said in the end, but you said that there was only one climate model available.
Yes.
Do you mean that it wasn't accessible for you, or what do you mean by that?
For the RISE-Q model, it was there's this meteorological database for Spanish area, and it was there was a weather station that only had this one predicted projection for this one model available. And then we weren't sure, is it okay to go further out than this weather station? Like, where do we make the assumptions? And that's where we would have to discuss with the experts like you what is appropriate to use, I guess.
Okay, a second question. When you say that it's too difficult, is, for instance, then ESGF, is that archive too difficult to understand?
I think so, yes.
Hey, thanks.
Yeah, thank you. Any more comments? Rasmus has a comment.
I understand very much that ESGF is difficult. I find it difficult too, but Copernicus, climate change services, because that is supposed to be more user-friendly. Do you have any experience with that?
No. I didn't look that much further. I had a look at the, what is it called? The Norwegian climate, I don't know, maybe you remember the name of that. Yes, we had a look at that, and for those projections, we would have had to do a lot of calculations for the evapotranspiration and the radiation and wind, and I'm not an expert on that, so it wouldn't be directly applicable. And there was a WISP model, so there we had really, really strict format issues with the input from the climate data, and then we just used the climate models that were available, that were already used for this model once before. So, yeah. But in future, we could look into Copernicus more and get those models as input.
Yes. Yeah, just when I deliver back, I think you're hitting quite straight home, because the entire leader group of the Norwegian Center for Climate Services is present in the room. So thank you. We really like to have the answer. Please.
So a quite technical question. In the Bayesian network,
yes,
how many do you know how many parameters you have approximately, and do you learn those parameters, or do you?
I'm not sure I
input them by
understand
hand?
what prompters are. I'm sorry.
So you have in the Bayesian network, you have like truth tables.
The conditional probability tables.
Yes.
Yeah, most of them are equations, so the distributions we get from the 26 years of peak concentrations we have, and then that was for the WISP model, and it's usually like an equation or a distribution that we have now as input to have those connections.
Okay, so
I don't know if that explained it.
yeah, so I guess you input like probabilities that you already have.
We derived them from the data, and we calculated, or we fitted the distribution to the data we derived from the prediction models, and that's what we used as input for the Bayesian network. Yeah.
Thank you.
Okay. Thank you, and thank you, Sophie. I think we are ending this part, and it's Rasmus that's going to lead us into the next group work. Yeah, I can open it here. There are 2 comments on Zoom. Yeah, we have time. Yeah. So, Andreas.
I'm not in Zoom, I only saw that.
Okay, do you have them?
I have Zoom here. So this chat. So Abdulkader Mesgani asks if you can use gridded data instead of weather stations.
Yes. Yeah. For Sophie.
But you need a microphone, so you need to come up here first. So can you use gridded data instead of weather stations?
Probably, yes.
And then Thomas Abebe Tegen said, thank you for your presentation. From nothing, one thing is good. When you pick one model for your analysis, how you observe uncertainty? Did you do evaluation of that model? Thank you again.
For the climate model, you mean?
Yeah.
Or for the prediction model?
I think he said pick one model. I guess that would be the climate model.
Well, as there was only 1 or 2 available, no, we just used them. Because it was more about developing the concept, and then now we can improve on it. Now we can run the prediction models on the basis on those new climate models, or better climate models, or samples of climate models. So it's not limited for that. We can still do that work.
Excellent. Yeah.
Okay. Thank you, and thank you again. I think we leave the floor to Rasmus, and can I get this screen up again? Yes, Rasmus.
So now we are on T5, so a little bit more work together. And one thing that we thought about was to maybe have some kind of positions statement from this workshop regarding how to use, say, downscale data, climate information for climate change adaptation and for engineers. And the other thing was how maybe we should we need to carry on this because we're just starting, like how to get funding to do more work on this, because I think that is needed, because we see that the world sees a lot of extreme events unfolding, and we are obviously not prepared for these events, like the droughts in Europe or floods in say, China or in Pakistan, or and droughts in the US. So we need the world needs to adapt to the present and future climates. And then we need to be prepared to be able to help and support that climate change adaptation based on the best information that we have. So then we need to do some more work. This is just starting, right? Because first of all, we should actually discuss whether we are in position that whether we agree that we are able to provide that information now, or if so, then we probably don't need to do any more further work in terms of trying to find that. But also, if we're not, then we need to discuss, okay, how to get there, and how maybe, and that work needs to be funded. Like Chris Leonard said, we can't work for free. We need to be paid for doing this. So it would be good to have some kind of status on that. And I think this is also part of the outcome of this workshop, is to have a stock taking of where we're standing in terms of the situation that we are in terms of being able to provide climate information for society or RIFs. And I think these last 4 talks have given some excellent examples of where we're standing and what we can do. But I think also it would be nice to see if we can also agree on maybe some take-home messages that we can take to the next year's Codex meetings and the World Climate Research Program meetings and so on. So then these are the things that I think we'll work on now. And it's, I think we have an hour or so. Let's see.
Slightly more than an hour.
Yeah. So we have some time to work on that, and then we'll wrap up, and then we'll have conference dinner afterwards, some of us. I sent an email around to ask like whether people are coming for the conference dinner, and I hope everybody who want to come have answered, because Christina had to give a confirmation, and I think we're about half or a third of what we actually thought would join for the dinner. So we need to change that number. And for tomorrow, I will also I'll send out a link to find out how many people are coming for the lunch tomorrow at and Portal. So it's not here. We walk to the we'll take a tram to another place, and then we'll have an excursion to see Oslo City Municipality, how they deal with climate change adaptation. For instance, green roof is one thing, but also how they manage the sort of flooding events and so on. Yeah.
I have to leave in the afternoon for the flight. So how long will it take, and are we far from central station?
So it will be a few tram stops from the central station. So you can join for lunch if you like, and so that it will be a bit further away. So it depends, depending on how much time you have.
But I think this is maybe for others also important to know where we are and how long it will take from there to the airport.
Yeah, so we can help you with that. So they run quite frequently, so you can take the tram to the main train station, and then, yeah.
Or airport express.
Yeah, it does that go from there? Okay, yes, excellent. So yes, so Habiba, it's the restaurant tonight. If you do a refresh on the website, I've actually added the address of the restaurant on the website.
So Habiba, wasn't it?
Habiba, yeah.
So that was
Habiba Oslo.
Yeah. Habibi, ikke Habiba.
Habibi.
So
yeah.
Yeah,
So
we're driving car, but walking it's.
We are here. Sorry.
It's 3 minutes walking.
Yeah. Okay, but let's. If you want to move around a little bit with tables and swap, you're welcome to do that. And good. Thank you.
Ja. Ingen svenska åker helt. Han ingen svenska åker.
Bare spør vi om hva det kommer frem til diskusjon og sånt.
Ja, så da kan vi kommentere litt hva jeg ser selv.
Ja.
Både på det her og sånn generelt på dagen, tenker jeg.
Har vi en mikrofon her? Nå blir det litt vanskelig med kameraene, fordi at de står siktet mot oss, så da det blir sånn. Shall we start? Okay, so this is the sort of final wrap-up, or the official wrap-up for today, because the unofficial wrap-up will be during the dinner, I guess. I would like to hear, I will share this microphone around, and I'd like you to talk about some of the things that you found most interesting or most important during the 5 different sessions, like T1 to T5. What you have come up with, like you can say, concentrate on the last one, T5, if you have that more freshly in your mind, or any of the others. So I'm going to pass on this microphone. Andreas, can you send it on? Or do you want to start, and then you can send it on to the other tables?
Nice, easy start. Yeah, I wasn't here all the time, so yeah. I thought that since I was involved in the presentation at tomorrow morning, I thought the T3 was very interesting to how to consolidate or use ESD and RCM together.
So this is like a topic where you think we also should try to put more emphasis on. I think this is probably also something that is more concrete, maybe more tangible, maybe, yeah.
Thank you. So I'm thinking that our analyses should be informed by user needs and user stories. So different users have different needs. For some of them, 12 by 12 kilometer temperature and precipitation is completely fine. Others, they need or they want finer resolution data, perhaps also finer timescale data. Some of them need bias-corrected data run through an impact model. And some users, they require bias-corrected data that are consistent in time, space, or between variables. So these 4 different levels of modeling chains will answer completely different questions. And I think it would be nice for us to give some guidelines on in which cases these could be informative.
So then another question to you. Have you asked them why do they need it, and also how do they use that information onwards?
It could be based on a compound event. Perhaps the health researchers need both temperature on cold days and pollution data. Then can we provide both of them, and do we ensure that the cold or that the high pollution actually happens on the cold days?
Yeah. But do you ask them how do they actually use that information? And also what happens if that information is wrong?
Yes, and the result or the answer I got yesterday is that so far they are looking at observed data, which is fine because then we have the time sequence in the perfect order. But the question becomes, what would we do in the future when the time sequence is scrambled?
But I would ask then, how do they use the observed data then?
But Rasmus, I'm going to challenge you because you have your mindset set on that. But there are people out, there are events out there are systems out there. For instance, I've been working very much with the building sector, and you can look at the decay of concrete decay. There typically you need water on the wall, and then you need a frost event. So that's when you need this time. You need the time sequence to be correct. And there are quite a lot of these models out there. But there are also models, I agree with you, where this is not important. So what should I answer them?
So I'm not saying it's unimportant. I just want to know, how do they use that data?
Yeah.
Because if we understand how they use it, maybe sometimes we can say, well, actually, we have something even better, right? So to have this dialogue and ask them and challenge them. Jannike, it's your turn now.
Yes, I missed parts of yesterday, but what really stands out for me from this workshop is the need for dialogue and collaboration. So this is like a first step towards more collaboration. Because I'm more from the user side, user of climate data for impact modeling, and like, sorry, I forgot the name, but like you just you gave examples of users need this and that and so, but many users don't really know what they need. They have a more vague idea. They need some kind of climate projection for, say, 2050, but some climate modelers have to tell them more specifically what, for example, how many climate models they should use, which scenarios, and so on. Okay, bye.
I'm just sending a bill, but continue. You can pass it on to Hanne.
Okay. He just needs to sign a bill for the food, but we know what you talk. No, or you can send it to another table.
Okay, so well, I thought the discussion today about the users was very interesting, and sometimes it's about like kind of interviewing the user sometimes to really get to understand what they need, and trying to really understand together like how far we can go with the climate information that we have. Sometimes it's really exploring together with the user their own, how their needs really combine with what we have, and sometimes we just have to agree that Codex is a little bit beyond the user needs, and maybe trying to find some other solution that is beyond Codex. Some other part that was interesting, or that we mentioned in, I don't remember in which group, was to somehow coordinate the development or the use of the statistical downscaling methods. That would be a good, I mean, maybe a big effort, and it doesn't have to be competing, but I think somehow have a coordination, because there are a lot of diverse methods. Maybe it would be good to have something, so we can do something on coordination. Some other thing, well, we found a paper published in International Journal of Climatology on CMIP6 models that were at the scale of 2.5 seconds and 2.5 minutes. They have many citations. They are from the University of California, and we don't know why they are not here. I don't know. Somehow the community is quite spread, and it would be good to just, I don't know, have more cohesion somehow.
Yeah, so next. So just a comment to that. Next year there will be two big conferences, like the International Conference on Regional Climates, that's the Codex, and then there will be this International Open Science Conference so one will be in Trieste and with a hub in Pune, and the other one will be in Rwanda, in Kigali. So there will be two big conferences, and we hope that these ideas will sort of feed into these conferences, so we'll continue that.
Okay, let's have a look. I've talked to some impact modelers, and I think it's very interesting to see how climate data is used. And like from our standpoint, as like I work with statistical downscaling, we downscale like 100, 200 simulations in no time, and then we hope that someone will use the whole ensemble. That's our recommendation. But then for like the impact modeler, that's just very that's not very practical, and that doesn't work with their workflow. And so I think it's obvious that we need sort of to have like one-to-one conversations, figure out how to actually use climate data in the most in a way where you like use all the information that's there. I also think it's been very interesting to hear how other people use both statistical and regional climate model data, as I'm trying to figure out how to use both and how to combine them now. So it's been good.
Please actually say your name as well. I probably should have said that in the beginning. So.
Yeah, then I start. Hi, I'm Raoul. I can just, I'm all on your side. So bringing together the communities, I think, is very needed, and I think this workshop was a start to this. So with different users, I mean, GCM community needs to be brought together with the RCM community with the end users, the impact modelers, but also connected to the large ensemble community, which I am part of, for example. Just bringing together all of them to then find, because there's so much data out there, we cannot all use all of the data. So we need to find the best usage of all of these different data sources that are then best suited for the application. So if we look at extremes, we should maybe look into using large ensembles more. If we want to quantify uncertainties, then we should look at multi-model ensembles. So giving a guideline on which data is out there and then for which purpose the data is best used. And then today was also eye-opening to see, so I'm an expert user of climate model data. And for me, of course, data is abundant, it's openly accessible. I thought it was easy to use, but apparently it is not. So we need to find ways to make it more accessible. So something that could be a good step is on top of the ESGF, we can add another layer where you can do simple calculations. For example, you just extract the data for your data point. You have already scripts that help you analyze or calculate mean values and things like this. So this could truly help a user to make that data more accessible.
I'm sorry, because I was just told that we should have been out 15 minutes ago, 5 o'clock.
Okay.
So there's been a miscommunication. So I think we'll have to continue tomorrow with the rest of it. I'm really, really sorry. So, so I think we have to clear off and because they're going to have another sound check apparently. So different sound people are coming in. But thank you very much. And also sent an email regarding tomorrow lunch to everybody who has actually signed up for the lunch. You see if you can respond to that, so then I know what the number is for tonight. A bit similar procedure as for the dinner.